Udah live streaming ya? Oh, udah di YouTube. Oke, selamat pagi. Assalamualaikum warahmatullahi wabarakatuh semuanya, Bapak Ibu yang ada di Zoom. Kita lanjut pada hari kedua. Katanya hari ini hari yang susah karena practicing bersama Python. Tapi dengan adanya guru kita Pak Hamed, insya Allah gampang lah ya. Kita diajarin sampai paham katanya. Oke, kalau gitu kita mulai sekarang pukul 9 kita mulai. Selebihnya kita ikuti saja demo dan practicing dari Pak Hamed dan Bu Cindy. Mungkin Bu Cindy ada yang mau disampaikan dulu?
Ya,
saya
tidak. Ya, maybe I'll share the screen. Oh ya, maaf boleh share screen.
Robi kasih.
Pak Robi, maaf. Ya, oke.
Dan Pak Hamed juga kasih kos.
Halo, selamat pagi semuanya. Hari ini yang Pak Hamed mengajar tentang beberapa aplikasi yang dibangun dari Radiant Earth. Tapi hari ini mungkin ada sedikit perubahan. Mungkin saya mengajak yang Pak Hamed bilang yang hands-on exercise yang berubah seperti apa. So I just told them that there might be some changes in what's been taught. So maybe you can talk about what you're going to teach today and what they need to prepare right now.
Yeah, sure.
Yeah.
Anything else I can do?
Yeah, I can stop sharing my screen if you wanna. You wanna share anything?
I can share with small. So I can. Okay. Yeah, so good morning, everyone.
Morning.
So I will send the link to this repo soon, but basically what I put together mostly for today is a little bit more intros on how the datasets on MLHub are cataloged, how we can access them. I will go through some of the details on the website page, so you know how to navigate a dataset, how to download it. Then we will get started with the Python client. So I will show how to get signed up, how to get your API key, and then I have 3 notebooks that we will go all together. The notebooks are hosted on this repo. I will put this link in the chat very soon now. I will go through how to install your local environment, all the dependencies you need for the Python packages to run these notebooks. The first one will be just a simple how to access a sample dataset, download some images. And then we will use QGIS, or if you have ArcGIS, you can use that to just visualize the data, see what is in there. So I had to make some little changes here. There was some issue with accessing one of the land cover net data, particularly the Asia one, using the Python client. You can download it through the website now, but our Python client was hitting an issue last night, so the team is working on that. But for the time being, I'm going to show the demo using the South America data. Again, how to filter data sets there and access some of that. Because of that issue with the land cover net, the training model part, I will show another example. Instead of land cover, will be a cloud classification problem. It's a similar kind of categorical problem. We have a sample data set again, Sentinel-2 bands and labels for cloud. I think after this, we will have a short break. And then the second part will be the planetary computer one, which I have a typo in there, definitely. We will go through a tutorial how to do kind of a scalable analysis on planetary computer, particularly using something called Dask. I will give more intro when we get there. But the idea is how you can basically scale your analytics using some of these frameworks out there, one of them called Dasks. So that's the overall agenda for hands-on tutorial today. The only thing you need before I start is having a Python installed on your machine. That's it. And preferably, that's not preferably, actually, that's the requirement. The Python should be 3.8 or later. So that's the only thing. I will put this in the chat now before we get started. So this is. Any questions so far before I start. Yeah, from there.
Ada pertanyaan dari Zoom participant atau di sini?
Tes suara, apakah cukup jelas suaranya Bapak Ibu? Oke.
Bagus. Oke, Pak Hari bilang oke.
Okay. So I briefly mentioned about this yesterday, but this is basically the ML Hub website. I will put it in the chat. The first thing you want to do, let me log out here first.
Recording in progress.
Okay, so when you land,
Sorry.
just okay, perfect. So when you land on MLHub.earth, you need to sign in to get an API key for basically accessing through the Python client. Let's do that first before I go through the instructions of how to access that. So when you click on sign in register, if you're already a member, you will literally log in. If not, you will just sign up. The sign up is simply your email, the password, name, country, organization. That's it. And immediately you will get your profile. So maybe everybody goes through the sign up and make sure if you have issues, there shouldn't be an issue. This is pretty much automatic. So go to mlhub.earth, the link I put in the chat, click on the top right, sign in, register, and then just sign up on the dashboard basically with your email, credentials, and name. Then I will log in and I will show you what I see.
Linknya mau Pak Owi?
Yeah. Because I joined chat late, so.
Oh, you don't see the intro?
Oh, yeah, maybe
Okay.
I'll do it again.
I can repost it. So
Yeah, thank you.
This one. This is requirement.
Wow.
I'm just reposting for people who join afterwards. This is badly, so it doesn't keep.
I will do that. I can help you with that.
I didn't mind for you yours. I can Okay, so when you log in, I'm going to show you and then pause again. You will see basically your account here, and you can access your API key and settings up here. I will show my API key, but we can't delete that because we'll show this recording later on. Basically, you will get this user and API key at the top, and you have more kind of legal stuff down here. You won't see this admin that is only for me, but this is what we need later on in the Python. Your API key when you log in. Keep that there. We will come back and basically copy this information later on. But let me go back to the data sets and pick up one example to give you a notion of what we mean by data sets and collections. Let me pick a simple one first. This one probably. So this is a sample data set. It's crop types in Uganda, for example.
Just,
Yeah.
I just sign up to the website, and then I cannot find the API key.
So did you log in? I mean, it automatically logs you in.
Yes.
So if you click on this three bar, do you see settings and API keys?
Settings and API keys, and then
You would see API there. If not, you can generate a new one. If
or
there's-
new.
Yeah, new
API
API
key.
key. Yeah.
Just click the.
Just click
plus.
that, it will automatically generate. See if I click on this, it will ask for a description. I can say
And
temporary.
we think never expire.
Never expire basically means never expire. So literally you can say no, never expire. So you can always use that. Or you can put the time bound on that. I mean, if you don't put it, will automatically put something. But we usually use never expire because this is not a like product or operational thing. So you would keep it all the time. Yeah. And if you have something you want to delete, you can later on delete. So there's no problem with that. See, I just created the temp. I can delete it right away. And only will keep the older one for me. Yeah, when you delete that key, it will be not active anymore. So if you have any pipeline using that key, it will be broken after that. So let me maybe ask a question. Anybody else having issue with signing up and generating an API key for themselves?
Siapa ada masalah untuk yang registrasi dan downloadnya? Ada orang? Kalau ada pertanyaan bisa raise hand saja. Kita bisa tunggu.
Di suara mute-nya di unmute aja kan semua. Bisa mereka bisa open mic. Oh ya. Nanti.
Ada pertanyaan? Apa? Oh, mau ambil API key?
Tadi
Betul, Pak?
jadi plus new API key.
Saya bisa bantu.
Oke. Oh.
The name, the description doesn't matter.
It can be anything. Yeah, it's just for yourself because you can generate unlimited number of keys and have them specifically for specific applications or products. So
Yeah, never expires. Oke, ya, no worries. Kalau ada pertanyaan bisa langsung itu tanya saja. Kalau ada partisipan yang baru, saya upload linknya juga. Bentar ya. Kalau tidak ada pertanyaan, ya kita lanjut lagi.
Yeah.
Yep.
cool. So back on the ML Hub website, I briefly showed this in many slides yesterday. So you can go to datasets page at the very top of the website and basically see the list of all the datasets, both their location, basically it's the center point of where the dataset is applicable on the map, some specific keywords, which is about applications, this type of sensor, like you can filter by Sentinel-1, by Sentinel-2, by NATE, which is the airborne immediately Landsat 8, or by applications like agriculture or land cover or flood detection, or just search for keywords here, all the different ways you can filter down the data set. Or if you know the specific data set, you can literally scroll down and pick a sample data set. I want to mention some of the terminologies we use here. So that's why I opened this sample data set for now. So just look at what I'm presenting and then we can navigate the website together. So when you land on the website page, again, you see the map and a bounding box of where the data set is applicable. You can zoom out and see even more where this is around the board. But this shows where the samples are collected. In this case, crop types on the ground. You will get a description, very high level, what is this data set about, how many fields it has, when it was collected, things like that. You have a documentation for the data set. So if I click on this, it will open a new tab. Actually, we downloaded it. So the PDF will contain various information about how the data set was collected. Depending on the data set, this documentation might look different. Who collected it, what was if it was image annotation versus ground referencing, the things will be different. But you get an overall detail of what is in the data set. You can see all the property, for example, values, their description. You see there's a lot of them actually here because they have done a lot of ground sampling for each point. What app was used to collect the data, what pre-processing or post-processing was applied, how the imagery was matched, all the details about any specific data set, right? So that's how you would use a documentation generally. And then we have this, so this is the term for data set. But then we have this notion of collection. And I want to make sure we are all comfortable with that. And this comes from how this stack, spatial-temporal asset catalog that I mentioned in the slides yesterday, defines the properties for each data set. So a collection is basically, as the name might kind of resembles, it's a collection of things. In this case, we have what we call a source imagery collection. So in each training data set, you have a set of source data, and then a labels collection, which is basically the target variables. In this case, our source imagery are Sentinel-2 images. Our label collection is basically the crop types on the ground. You can see again more about this in the documentation. But when you interact with the data set and you want to download things, you will get this notion of collection. So usually we have one source imagery collection and one label collection, but you can have as many of them in any training data set. So you might have one target variable collection, so one label collection, but two source imagery, for example, Sentinel-1 and Sentinel-2. Or you might have multiple labels. I will show examples of that right now. But that's what the general labels mean. If you are logged into the website, as I'm now, you can literally download the whole data set right here. But as you see, the size might be a little too much. In this case, the source imagery is about 60 gigabytes. This is an archived folder, all the time series of Sentinel-2 chipped for this region applicable to that. The labels are definitely light because there are not that many of them, so it's just 200 kilobytes. It's just basically target variables here. You can also click here at the top and download the whole thing together, or you can get what we call stack catalog archive. I will show this in the Python client. Don't worry about it at this time. Any questions on the notion of collections, data set, what we mean by each of these before I move forward? Sure.
Both the licenses.
So the license you see right here. So each of these collections will have a license, which basically tells you how you can use this data set. They are all open access, so they have some level of open usage. The typical one we use is this CC means Creative Commons, which is the organization puts many of these open license things. By means by attribution, so it means you can use the data set if you attribute, if you cite the data set. In this case, it's CC by SA. CC by SA means share alike, which means that if you use this data set, the product you derive from that should be also open access. You can, for example, use it for a commercial application. Share alike means share it alike the source. The source is open, you should also do open source. These licenses are decided by the data provider, not us. In this case, for example, the data provider is Dalberg Data Insight. We just helped them with the cataloging. And they decided to go with share alike. Majority of the data sets don't have the share alike thing, which means you can literally do anything with the data, commercial, non-commercial, as long as you just cite the data set. Say, hey, I use this data set, this is the application, and this is how I use it. So that's the only requirement here. Yeah, but all of them are at least open for research and non-commercial application. That's the bare minimum on all of these products. Otherwise, you wouldn't be able to access them. Yeah.
So if we share the data, as long as we follow the license.
It's okay. Yeah. Each of these, we are going to actually in future add a hyperlink to this. But if you search this, there is a good description of this license. So CC by SA4 has a good description on their website. What does it mean? What you can do? What you cannot do? And everything like that. Yeah, this is one of the principles we follow. The license should be there, so the user is well aware what they can do with the data, what they cannot. Because you literally don't talk to anyone. You access the data and you can use it. So you should be given information how you can use it for our application and things like that. Any other questions? Anything in the chat? Okay.
Kalau ada pertanyaan bisa langsung tanya saya private DM di Zoom saja. Terima kasih.
So I'm going to show another data set. So
My question, Mr. Ahmed.
Yes.
Can we already use the data in your cloud without downloads? Like we using script, like in GAA, we using script in Java. We only type the IMAC ID of the data, and we can directly to read data, to process data. So for this link, Radian Hub, if it's the same thing like that.
Yes, so basically, the way you can access the data, I can go back to the docs page. I wasn't going there yet. We have a Python client and we have an API. The Python client is basically Python specific. If you are coding in Python, yeah, but if you are in Java or any other programming language, you can use our API. So under the docs, there's an API documentation. So you can literally write your own API calls and access the data the same way you would use it in a Python client. But there is no client written for that. So you have to write your own functions and things like that. But all the functionality is available in the API that we have in the Python client.
So we should install a Python library to connect the Radian.
Yeah, I will show that later on. So after this, we will get to using the Python client.
Oh, okay. Yeah, maybe we should practice, I think.
Good. Okay, so one thing I wanted to show was this is another sample data set. For example, it's called the Fusion data set for club type in Germany. We have also a similar one in South Africa. It's a fusion, as the name says. So you have multiple source imagery here. And for that reason, we have multiple source imagery collections. So in this case, we have planet source imagery for training. We have planet 5-day imagery, which is the composite imagery from planet for training. We have the Sentinel-1 imagery for train collection, Sentinel-2 imagery for the train collection. And then we have similar ones for the test, because this was originally split between train and test in the notions we have in machine learning. So we have actually 10 source imagery collections just for one data set. Because it's fusion, it is multiple data sets. And for labels, we're going to have the train labels, and then we have the test labels, again, 2 separate collections. This was part of a competition, so that's why we split them between train and test from the beginning. But otherwise, you can use them the same way.
For those who use ML, could you tell them why the training test?
Oh yeah, so why we have train and test, and what does it mean? So when you build a machine learning model, I had a simple slide yesterday, right? So you only use data and some architecture to find parameters and coefficients for your model. When you're building that, you use a set of data, we call it train or training data set. In that sense, you iterate through those, you have a loop, you find the best parameters for your model. But to make sure the model is doing good and it is not what we call overfitting your data, you usually have a separate collection of data, we call it test data set, which after the training part is done, you would go and just evaluate the performance of the model on the test data set. That will tell you a little bit how good is the model. Does it overfit to your training data? If it does, what should you do? How you should go back and change your basically training pipeline or model architecture. So for that reason, you usually have at least 2 collections, train and test, that would give you that performance metric. In dataset competitions, usually the test data are private. So you're building a model, you submit your solution to the competition portal, they test that against your test data, or sorry, against their test data, and then they will come up with the scores and put it on the leaderboard. So that's how the competitions usually are run. Post-competition like this one, we also release the test data so everybody has access to that. But that's the general notion for train and test collections.
Questions
Yes.
on the difference between CC by YSE 2.0 and 4.0, and then later there is a DDDL.
Yeah. These are all the legal terms. So each of these data sets collections is coming from a different institution. So they pick different licenses for these. The 2.0 and 4.0 and C, some of these are actually CC BY, so there's no share alike besides the Sentinel-1, Sentinel-2. It's very, I think, minor changes between 2.0 and 4.0. It's more honesty on the legal terms when you read through them. The baseline is you can do it for anything which is open source. But for legal purposes, again, you have to list everything as detailed as that. This one is a German license. It literally means the same thing. But it's just the German terminology for that license.
Okay.
Because the data provider was German, they picked the German license. But as I said, because you're accessing this literally for free without anybody gatewaying that, they have the minimum open source thing for research and non-commercial applications. So you can be almost sure there's no problem for using that. Whenever you want to get to commercial, then yeah, be concerned with looking at the license. But in any case, you have to cite them and reference the data set. That's always required. And that's why each data set has a DOI and a citation listed here. So these were the two topics on the agenda. Then I can go to the Python client. Any questions so far on this before I jump on the Python client?
Few participants, so maybe just reiterate that you can look at the chat to register.com.
Oh yeah, so yeah, Cindy is reposting the discussions we had earlier. We basically went to the mlhub.earth, used the register sign in option at the top, unlocked in so you don't see that. Signed up, so created a new account with simple information there. And then when you click on your headshot here, you will see settings and API keys. And that's where you can use this new API key button and generate an API key for yourself. That's what we'll use later on in Python client. So
Hamed,
make sure
sorry.
you follow that.
I just follow Cindy's instruction to sign up to the website, and then I check my email, and then I have an email from you. Is it okay?
Yeah, that's probably welcoming you to
Yes,
MLHub.
welcome
Yeah.
to Retrieval.
I didn't type it now, but yeah.
So it's your robot, yeah.
My robot, my bot.
Avatar.
Yeah, I have a bot sitting somewhere. doing that. That's a very old email. I haven't checked it. Hopefully, information is not there. But anyway, it's just welcoming today. Again, there's not much happening. So the next thing is getting started with the Python client. So again, under the docs, you will see the link for the Python client documentation. This is basically the easiest way to access data sets beyond downloading from the website. But the website thing is limited with the size, right? If you have a 10 gigabyte, 20 gigabyte data, it will take forever to download. So we would always recommend using the Python client for accessing the data set. So if you click on the documentation here, this is where you will land. Those of you who are familiar with general Python packages, they all have a similar template usually for their documentation. This is where the MLHub documentation comes in. I'm not going to go through everything here, mostly about just setting up the environment. Then we'll go through the Jupyter notebook with examples. But the main thing you need to do is have a local environment with Python 3.8 installed, so you can easily install the Radiant MLHub basically package, and then use the tutorials we're going to go through. The installation is either through the pip install or the Conda forge basically. So any of these two commands you can run depending on what type of Python you're running locally to install the latest package for Radiant MLHub. You can either do this, or I will go back to the Jupyter notebooks. We have a requirement file there, you can use that. But basically in your, either if you're in Mac or Linux, you can use the shell, the terminal shell script, and in Windows you can use the same. What is it called in Windows? I forgot. Old days. There's some way to do this in Windows. I forgot what is the. It's not called terminal, but the same thing. You can literally use this installation again, either Conda or pip to install the package. The next thing and the main thing to do before we get to the notebook is configuring your API key. You can skip this for now because in all of the notebooks, we have a cell that you literally paste your API key and start using it. But generally, you can go to the command line again. Let me actually zoom in here. This might be a little small. Yeah. You can use the MLHub configure command and enter your API key. that would be registered in your system keys, and it would be there forever. So you don't need to paste it in your Jupyter notebook each time you're using it. That makes it just more convenient. Otherwise, the same functionality is available in the notebook itself, and you will see later on. So that's the two steps: installing the package and configuration with your API key. That's the only thing you need to get it started on the Jupyter notebooks next. So I will pause here and ask everybody to install the package, or at least those who want to follow us on the Python, to make sure everybody feels comfortable. If you run into any issues, please put it in the chat. But the installation should go smooth. There isn't any specific requirement other than, again, Python 3.8 is the minimum required. Again, because of all the dependencies we have, that's the only thing.
I have an error. Each dependency resolver does not currently take into account all the packages that are installed. This behavior is the source of the following dependency conflicts: Conda repo client 104. Because I installed Python 397.
That's okay. 397 is okay. But did you install it in the? Did you create a new environment to do that, or it's just the root environment? You know the notion of environment in Python, or should I go through that?
Maybe go through that.
Yeah. So let me do something here. That's probably best to bring up something. Let me first explain. So when you install Python, you have an installation, an instance of Python on your machine. And you can install any packages you want in that instance, from RateNML Hub, from NumPy, from Pandas, many other packages, the machine learning ones. But the more you start adding this, the more these packages will have conflict between their dependencies, right? Because they require different versions. And that's where things will break. And it's the nightmare for programmers to do that. So Python has a notion of environments. You can think about them as different instances of the same Python version installed on your machine, right? So you have environment, let's call it 1, which is an isolated installation of Python, and you can install specific packages there that are relevant, for example, for today's project. You can have environment number 2, which would be specific for a project you have next month, or at the same time, or they're running, and you would name them differently, right? You can, for example, I created an environment last night called the Brain Workshop. So I know this is for the thing I'm doing today, and I install packages related to that. I'm not breaking all the other dependencies for 10 other projects we might have. It is highly recommended to use these environments regularly in Python. They sometimes are called virtual environments, sometimes they're called environment, but it's literally the same notion. There are 2 ways to install or add a new environment. If you're using Conda or Anaconda for the Python, it's literally one command. I can show you here, Conda create a new environment. Let's remove this. I will put this in the chat as well. This one. So Conda create name of the environment. That's it. Let me get the link to this one. And then you would name it whatever you want. Here is called myNav. You can enforce the Python version there. So in number 3, you can see a specific version of Python. So that's, for example, specifically what I did. I say Conda create. The name would be bring, for example, Python 3.8, 3.9, or whatever you want to do. And that will create a new Python environment for you. Following this page, you will see how to activate that environment as well. Activate an environment. So when you have an environment locally, you want to make sure you basically go to that environment before installing packages. And that would be Conda activate the name of the environment. So let me put it here. Here you see Conda activate, for example, my environment. I will go to terminal and show how I do it on my machine as well. And then if you're using the typical Python installation, not the Conda one, there is also a virtual environment command there, which is I usually recommend Conda. Yeah, Conda makes your life easier. So this is how you would do a virtual environment in a typical Python thing. You say Python 3, my environment, and then you need a path for this. So in Conda, it automatically stores the information in a path itself, but here you need to literally pass the name. So Python virtual. Same way you activate it here, and you will be good to go afterwards. Again, this is best practice. It is not required, but I would highly recommend using it because it makes package installations much easier and it doesn't break your dependencies with other projects. So let me go back to terminal and show you how I do it here.
Yeah, demo on terminal both.
Yeah. Okay, I need to share the whole screen. That doesn't give me 1 second. Why it doesn't show? Okay. Okay, so definitely increase the font size. Okay, so I have a Conda installation of Python, and when you navigate to your terminal, you will see the name base. This is the name of the environment, basically. And let me do clear here so you don't see too much information confusing. So when you go to your terminal, you will see the name of base here. I can say Conda create name. I'll call it template so I know how to remove it later on. And then I will say Python equals 3.8. So this will create a new Python environment called template with Python 3.8 install. And if you hit enter, it will basically collect the packages, look at dependencies. It will install the basic packages of Python, which you would need for running, like pip, Python itself, setup tools and things like that. You would say yes, because you would require all of this. And it might take a minute or so to basically run all the packages, depending on the internet speed. This might take longer or shorter. After it's done, it will itself verify that the packages are installed completely, and then I can use Conda activate. So when you're done, actually it gives you the instruction here to activate this environment. You can use Conda activate template. I use template as the name of my environment. So Conda activate template, and you will see the difference now. Now it says template as the name of my environment. Previously it was base. So now in template, I don't have any packages installed other than the basic Python packages. Anything I want to install will be a fresh installation here, and it doesn't break any other dependencies as a base. So create as many environments as you want. Just show you, if I say Conda info ends, oops. Oh no, this one. This will show the list of environments I have. For some reason it doesn't show them. Oops. Anyway, oh, I know. It doesn't need this. So this is the list of like environments I have locally for different projects, for different things. I have a different environment all set up. And depending on that, you would just activate that environment before running your Python script or Jupyter Notebook for the matter. So this is again best practice. Definitely follow that. Make sure you create these environments to make your life easier first and most. So I'm going to navigate to my environment for today, which I call the brain. So now I'm under brain basically. Any questions on the environment setup so far?
I think it might be online, like trying to figure out how to download stuff.
Yeah.
Um,
You want to be also cautious of
yeah. Run it.
it. They don't need to run it. I can run it on my
Okay, all right.
Yeah.
So if you have, kalau ada pertanyaan nanti bisa tanya saja lewat Zoom, bisa DM saya. Tapi sekarang kami yang melanjutkan tutorial saja, karena yang takut waktunya tidak cukup. For in-person participants, Robbie, can I assign you to help everyone, including myself?
Cindy,
Yes.
my question. Ini installnya standalone di desktop komputer masing-masing ya atau gimana?
Komputer masuk.
Harus Python version 3.10?
And above.
Langsung install Conda ya?
Yeah, you can either download the Python or Anaconda client, but Hamed recommends using Anaconda. So if you have downloaded a Python client,
Small Conda is enough, Hamed? Kan there are some Conda version. If we only install small Conda, is enough or not?
Oh, Anaconda, the same Python version. So 3.8 or above, anything under Anaconda or even Mini Conda. You know, there are Anaconda and Mini Conda. Mini Conda just have fewer packages. But 3.8 and above, any of them would be good. You can install literally the latest one and it would be all good. But if you have an older one, 3.7, 6, or 5, yeah, they won't work. But if you install something today and just use latest from Anaconda, that would be all good. Yes.
It's better to complete Conda version. Okay, thank you.
So we'll just continue now the workshop if that's fine. Kalau ada pertanyaan yang bisa DM saya saja. Terima kasih.
So this is the repo. I put in the chat earlier, but I'm going to put it again just in case, where I have all the notebooks for today. This is public on our GitHub repository, ML Hub tutorials, and there's a specific folder for today's workshop. So you can either just clone this repo locally or just go to the root and download this. You can see here code, and you can literally download the zip locally. If you're not set up with Git, just download this whole thing locally and then open the folder. But otherwise, you can also use the Git SSH command in your repository, in your local basic machine. So the way you do that is basically, let me open a new terminal. Downloads. So if it was new, I just navigated to a temporary folder. I would go here, get the Git basically link, and if you have Git installed locally, you say Git clone and the link that you want to do. But otherwise, you can just download the zip from the website and unzip it locally. You don't need to have Git installed here. But when you do this, this will literally copy everything from the website, put it in a local folder to your machine so you can access everything. Password, password, but it's worked well. So feel free to use either Git again or click on the code, download zip, and literally you have all the codes locally. This it's a little delay. Yeah. Here you can download the whole thing. And so when you download the folder locally, you would need to install, if you haven't installed the Python environment yet, or to make sure basically you have all the dependencies, you would need to install the packages we recommend. So inside this repo, the one that you just downloaded, and I'm navigated to that on my basically terminal, ML Hub tutorials folder, there's a requirements.dev file, which has all the packages needed, including the ML Hub client, NumPy, and other stuff that would be needed, basically. We would recommend doing the installation before running the Jupyter Notebook because all the packages should be available. The best way to do that is in the README file right here. So navigating down this page, you will see run locally. Create a virtual environment, that's what we just talked about. And then install dependencies, which would be pip install -r requirements.dev.txt. You would literally copy this command, come back to the terminal, paste it here. I'm not gonna press enter because I've done this last night, but literally this will install all the packages needed. Again, if you create a new environment and you do this, you wouldn't run into any dependency issue because it's a fresh installation of Python basically, and it would install all the packages. If I press enter here, it would just say everything is installed. So all the requirements are satisfied. You see requirement already satisfied, requirement satisfied, requirement satisfied. But if it's a fresh environment, it will basically install everything from scratch. So, okay.
This is your number 4, right, for agenda?
Going back to the agenda on number 4, yes.
Yeah.
Go back to the workshop. Yeah, we created this. We are doing the local environment and installing dependencies. Yes. Yeah, we'll pause for a minute because this installation might take a minute depending on your speed.
It might be the case that not meant to download the virtual environment yet, but it is okay to proceed and then we can come back to it later
Sure.
on after the workshop, right? Because I know you want to show a few things.
Yeah, so I will then run Jupyter basically and jump into the notebooks. So after installing all the requirements, I basically run Jupyter. You can run Jupyter Notebook or Jupyter Lab. Jupyter Lab is just a little fancier UI. It has this basically file explorer to the left. It makes your life easier in that sense. But Jupyter Notebook or Jupyter Lab both have the same functionality. So I'm inside the 2022 Bring workshop thing. So I already see the 3 notebooks we wanna go through. I will start with the easy one, which is browse and download a sample data set. So let me make this smaller. Zoom in a little bit. So the text is what I'm going to talk about basically, but you can read through this yourself later on. It talks about where the documentation page is, what are the dependencies, what you need to install, literally all the steps that I just explained, the virtual environment and everything. You need an API key, we already did that. You go to the website, you get that key. You configure the API key locally, or from here on that we have the code, you can literally paste your API key here. And it will work the same way. Let me do that because I need the API key. Actually, I think I can skip this because I have set it down already. Yeah, for me it should work because I already have installed. So these are the main things on the Radian ML Hub. You import this package. We are getting 2 modules out of Radian ML Hub. One is for data sets, one is for collections. We'll mostly use data set, but I also imported collections. The very simple thing is just listing all the data sets. The same thing you will do on the website. You can do it here in the Python client as well. Say dataset list and then print everything. If my authentication goes well, yes. So what you will see here is text. Can I get rid of this thing? Yes. Okay. Basically, you see the dataset ID, the name of the dataset. So each line is a dataset. This is UMD Mali crop type. It's the 2019 Mali crop type training data. This is Microsoft Chesapeake Bay. This is the Chesapeake Bay land cover training data. So you have the ID of the dataset, then a quick description of that. We have the 5 land cover nets that we just talked about yesterday for Africa, Asia, Australia, Europe, North America, and South America. Many other crop types. We have the SpaceNet one. Some of you might be familiar with. These are some open high-resolution imagery with building footprints and roads labels from different SpaceNet competitions. Tropical cyclone, soil moisture, and other kind of categories. So I think we have about 37 or 38 data sets as of now, but this is growing. So you can skip that and just get your dataset ID from the website, or you can literally look through this and say, oh, I want to, for example, use CGIR, East African Agriculture dataset. What you need is the dataset ID to interact with it in the Python client. In this case, I'm picking one of the NASA datasets, NASA Floods version 1. And this is what I'm doing here. So in the dataset module, you can fetch a dataset ID, get the actual dataset, and I'm just printing some of the properties of the dataset. So what is the title? What is the DOI? What is the citation? What collections are available in there? So the same content I was just showing you on the website, you can literally explore in the Python client in a programmatic way. All the content is recorded in the metadata. And honestly, that's how the website is populated. So the website is also looking at the database and populates that page the same way that the Python client accesses this content. Any questions so far on the very basic methods in the Python client? Basically, getting the list, using one of the dataset IDs, fetching the content, and printing some of the properties or high-level descriptions. The next part would be basically downloading the data. We call it assets in this case. This is again another terminology from Stack, because so you have the dataset notion, then you have collections. In each of those collections, we have assets, or more specifically, items that have assets. Item is one chip, for example. One 256 pixel chip can be an item. It has a bounding box where it is located on the earth, what time is applicable to that, what classes of labels are in it, and so on. And the asset for that is basically the file object that would have the labels stored in it. And here our goal is basically looking at that basically NASA Floods data set and the label collection. So you notice it has a source collection, it has a label collection, and download some sample files. What we do here is you can define an AOI. AOI is any bounding box on Earth that would be covering your area. There are, I would say, numerous ways of getting this AOI. A very simple one is this website, geojson.io. Let me put this in the chat. AOI bounding box. So you would navigate anywhere on the map. Let's say we're here. We're going to do a bounding box over Jakarta. You just use this drawing box. This is the bounding box. You just copy that, put it in your code. This is for visual things. Sometimes you might read this from another file. You have it in your code, or it's coming from another product service. But if you're doing data exploratory and you just draw a bounding box over your area of interest, you just navigate to geojson.io, use these shapes, get these coordinates, put it in your code. That's all it's needed from any geospatial package in Python. You can paste this and it would be good to go. They follow the same format in terms of latitude, longitude, orders, and things like that. So it's all good. I put it in the chat. It's geojson.io basically. Because I know where the data set is, I've already put a AOI in this notebook. This is where I'm interested to find some assets in this data set, floods data set. And this AOI, just so you know, it's over Bangladesh because the data set has samples there. I'm also interested to only get scenes from a specific time. So I looked at the documentation. I know this data set has images over 2017. So I pasted the month of June to see if any samples from June is available in that data set in that AOI. The last filter, if you may call it, I'm passing to this, is for labels. I want the raster labels, which is basically the same chips with the flood, no flood labels. And then from the source, which in this case in the documentation says it's a Sentinel-1 data set, I only want the VB band. I don't want anything else. Just again, subsampling what I want to select from this data set so I don't download everything. So if I run these two, the filter is defined. This is where the whole download thing will happen. So we had fetched the data set at the top, right? You remember here, this is what is the data set. We fetched it by the ID. Now I'm saying, okay, data set download, and I will pass these properties. Intersect with the AOI, so I want only chips that are available or intersect with my AOI. Date-time, this is the start and end date I pass, which is the first day of the June and last day of the June in 2017. And then collection filter is these two, basically what type of properties or assets you want to download, the labels and the VB band. And if I click this, this will start looking at the catalog. Oops. I might have, yes, my API key is also, let me add my API key. I know here, I deleted my own. Let me paste my API key here. Okay, this should work now. So one thing you probably noticed is that until the time you want to download the dataset, you don't need to authenticate with that API. That's where you would basically are required to have API key. And honestly, this is just a legal thing because when you do get the API, you check those boxes, terms and services and policy. It means you follow the license, you do good with the data, you don't harm and things like that. There's nothing else about that. And we just use that to derive some overall statistics, how many users are downloading. We don't look at individual downloads. So that's why you need the API key at this step, but not before that. So that's what is happening, guys. So it fetched the whole catalog. It was just 22 kilobyte. It unarchived it. I will show you what's happening. And then it's now downloading the assets that are relevant. So 50% done. It has found two assets or two files that are relevant to our filters that we passed. While this is downloading, I can show you what's happening in the file folder. So here, oh yeah, sure. Let me pause here now. Yes, so that's exactly what I wanted to go. Question number one, is it directly downloaded to your local computer? Yes, you will see these two folders were just added to my machine. One of them is a zipped or tar folder, which is basically the whole metadata of the dataset, not the dataset itself. Then the client is going through that and only downloading assets that are relevant to my filter, which is the AOI, the time bounds, and the asset types, which is the label and the source. So yes. Is there any size limitation? No, you can download unlimited data here as long as your internet connection is good. If internet connection breaks, this will retry automatically. If you fail, your Python stops or anything, but you keep these folders here and you rerun this cell, it will look locally to see how much it has downloaded and it will download the rest. So all of those methods are embedded into the client to make life of everybody easier. Is there any maximum quota to download the dataset? No, there is no limit. You can download as many times or as many datasets you want to download. That's the nice thing with ML Hub. So someone is paying for it. So there is no limit on any download, any size or anything. Yes. Just know this is sometimes it's confusing. This is only training data. So when I say Sentinel-1, it's only the Sentinel-1 scenes overlapping that training data area and applicable to that. You can't go and download the whole Sentinel-1 collection from us. it's only those Sentinel-1 scenes that are applicable to those labels in this collection that you can download. So that's the only thing to keep in mind. Sometimes you feel, oh, it's Sentinel-1, I'm going to go and download the whole thing, but there's no other Sentinel-1 in our collection. It's only the ones that have relevant labels in these data sets. So you say the download and finish, or no, it's still going on, but one of the assets is downloaded. So this is how the folder will look like. Maybe I can go over actually determine this one. It's maybe easier. Where is that? Many projects. Tutorial, brain, massive plus one. It's good enough where it's too small.
Yeah, so
How do you
view.
there's nothing. Show view options. Take size, yes. Okay. Not more than 60.
I'm on the
Right, that is better than the thing. So this is the content in that folder, right? So these are the notebooks that were already there. This is the zip folder. This is automatically unzipped. And literally in here, you have the whole label collection and you have the whole source collection. All of these, if you navigate to them, each of these subfolders is one chip in the data set. And each of them have a JSON file, which is how we record the metadata. If I open one of these, you will see what is inside them. But it's just the metadata, it's not the actual object, right? Metadata is, okay, the bounding box of this chip, the mode of the Sentinel-1, the frequency, the polarizations that are available, the links to the catalog itself. And these are the what we call assets, the BB band, VH band, and documentation. This link is literally a public link to a cloud bucket that would allow you to download the data set. What the Python client is doing is reading through all this data, kind of metadata for you and doing the downloading. But otherwise, if you're interested to navigate the documentation, sorry, the catalog yourself, you can do that too. But you don't need to. This is just stored in the metadata. The client is already doing that for you. And this is more information about what stack properties are being used, what is the name of the collection and everything. So this is just the catalog, just so you know what is in these JSON files. But otherwise, this is where it is being downloaded. So this is the BB band for this chip that we selected. It is applicable to our filter, so it's being downloaded. If it is not completed, yeah, it is actually completed. So going back here, you will see the whole download is completed basically. It downloaded 2 assets, which in this case, I know it is 1 label and 1 source collection data. And in this case, only BB band. If I had put VH, it would be 3 files basically. And I'm going to open this in QGIS to see what we have downloaded. But the same thing is available in the labels collection. So there's a TIFF file, which is the raster label for this thing. So let me open QGIS to see what we have actually downloaded. You can use any program here to explore these files. You can use Python, you can use ArcGIS, QGIS. These are basically GeoTIFF files, the raster formats typically used with many satellite data or broadly speaking, geospatial data. While this is coming up, any questions? Can you talk about the stack? What is it? I can quickly talk about the stack while QGIS is coming up. It's basically a specification on how you would record your metadata, as simple as that. It's a community-driven open source thing. Many data providers are using it. We have been leading that community, so we use it internally as well. So it doesn't discuss about data format, it's about the metadata itself. That's the only thing about the stack, yeah. But generally, we use GeoTIFFs and cloud optimized GeoTIFFs for the data set format and things like that. So this is my QGIS. Let me look this these tabs. I'm gonna just drag and drop this label raster here, and you will see it loading now. So this is the basically flood labels from that data set. In this case, I know from the documentation, 255 means flooded, 0 means not flooded. So the white pixels, which as you see, it's overlapping a river pattern, are water areas, other ones are not. If I open the VV band, which was the source data, you can also literally overlay that here. It will take a second. So this is the raw data set. So this was the VV vertical polarization of the Sentinel-1 data. And the data provider is saying they use this source imagery and they label basically what are pixels, which are these ones. So these are overlaid on top of each other. So we literally use the Python client, filtered an area, got these two assets downloaded, and this is the chip for you to build any model you want to do using this. The critical thing is here, before using the data, definitely read the documentation. So you better understand how they generated the labels, what is the definition of water for them. Sometimes they think about water seasonally, sometimes about scene-based. So everything is there. It's just you as a user need to educate yourself when you're accessing this data. But otherwise, the data set is literally applicable, available for anyone to explore and use. And you notice that the downloading option is pretty easy, honestly, in Python. Given the complexities of Python, we have added a lot of functionality into the Python client to make it easy. So I hope it's attractive enough at this time to try it out. So let me pause here before jumping on the next notebook to see if there's any question.
Daniel has two questions. One's about what stack and some other questions.
I mentioned briefly about the stack as we were doing this again. Have features for data version control. So Stack has guidelines for that, yes. And the way on ML Hub we are doing it is basically for each version of the data set, we create a different collection. And that's why you see these names V1 in the dataset ID. So this is the first version of this NASA flood dataset. If we create a version 2, a V2 will be added. The dataset collection will, basically the ID will change. And then we are adding what we call relative link in the dataset metadata that oh, there was a previous version and you can programmatically read that from the metadata. So that's how Stack defines the version controlling on the data. At the end of the day, it's up to the provider to make sure when there's a new version, they create a new DOI, a new ID, and link it appropriately to the other ones. What is the dimension of image chips if the analysis in a small region? So the size of the chips in each dataset is different. It depends what the data provider is giving us. In this case, I think they went with a relatively large one we can see here. Somewhere here I can see dimension. Here it's 11,000 by 12,000. It's basically one scene of Sentinel-1 that they have put it in a rectangular shape. So they didn't do any chipping in that sense of the machine learning board. Some of our data sets, I will show you one after this for the cloud cover detection, are literally chipped at 512, 512. But usually what happens and what we enforce is the chip size is constant in the data set. So if you have, for example, this floods data set, if you download different assets, they are all the same size. They are not the same size as another data set, but within the data set itself, they are consistently the same dimension. So if you want to use just that dimension and put in your model or chip it in a kind of standard format, you can do that within the data set itself. So that's what we enforce to make sure within the data set you have consistent dimensions for all the assets. Any other questions? Should I go to the next notebook? So I'm going to skip the second notebook and go to the third one, which is the modeling one, in the interest of time. But happy to basically go through the second one if you want later on. If you see here in the README, I have, let me open the README again. So this is the first one we went through, number 5, browse and download a sample dataset notebook. The second one was just the land cover South America. Again, a similar way of downloading the data and looking at it in QGIS and things like that. The third one is training a simple model. I would rather go through this because it's different than just downloading a data set. You would see how you can create a baseline, very simple kind of pixel-based model And then if we have time, we can go back to the South America one with the land cover. So this is the third notebook, Radian ML Hub Simple Model Training, I called it. Let me close this tab. Let's go full screen. We're already full screen, right? So the same instructions here, dependencies that are needed. Because this is a model training, we need some more packages, and we didn't install it at the root. So I added just the pip3 install in this notebook, that you can get the PyTorch, the Takadam, Rastrojio, Matplotlib, Scikit-learn, and Seaborn. Those of you who are familiar with machine learning, you know these packages, but broadly speaking, Torch is the PyTorch, the machine learning client that you would build and train a machine learning model with that. Takadam is just a visual thing for iterating through different items in a list and have a status bar. It's just for visualization. Rastrojio is a geospatial package. It's basically raster IO, means input output raster data. So you can read any kind of geospatial data with this. We use it to load data into the PyTorch package. Matplotlib, a typical plotting function and module in Python. Scikit-learn is another machine learning package. In this case, I'm only using it for confusion matrix analysis, but the actual training will be with PyTorch. And Seaborn is another visualization package similar to Matplotlib, but it's good for the confusion matrix at the end. I'll talk about that later. So just make sure you run this cell when you get to this notebook. Okay, again, I've already run it, so you see all the requirements satisfied, but otherwise this will install these packages that are required in this Python. The same instruction for API key, making sure you have that. And if I have the right one, yeah, I should enter my API key here as well. So similarly, we are going to pick another data set here. In this case, it's a cloud detection data set. Let me go on this one and show you what data set it is. Also, I can click on cloud. There is these two data sets. The one that I'm going to use is this one, cloud Sentinel-2 cloud cover segmentation data set. So this is basically pixel annotated labels for cloud cover in Sentinel-2 imagery. As you know, cloud cover is obstructing you from seeing the surface, so you would always want to filter it out from your image. So that's what this data set does. This is actually a Radian training data set. We went through two steps of generating this. First, crowdsourcing, and then validating those crowdsourced labels using an expert set of labels. Again, a good documentation with the data, you can read more about it. But my goal is to pick some examples from this data set, very few of them, not too many, just build a very simple model and then look at some performance at the end to show you how you can start from a simple data set and train a model, basically. So back here, I went to geojson.io, define an AOI I was interested in. Here you can see again the model, the data set covers a lot of regions. Basically, it covers South America, Africa, most of Australia, and a little bit Southeast Asia. That's where we sampled Sentinel-2 scenes for labeling. But at the end, it's cloud cover, so there's not much. I mean, there are differences in clouds, honestly, but when you pick such a broad region, you will cover many of the types of clouds. So this is an AOI, the similar pattern that I used in the previous notebook, right? You want an AOI where you want to download assets. Here, I copied the dataset ID again from the website this time, imported the dataset module, fetched the dataset, and passed these basically asset types to the Python client. I want all the labels, and from the Sentinel-2 source data, I want the bands 2, 3, 4, and 8. These are the 4 bands actually available. Why these 4 bands? These are the bands that are 10-meter resolution in Sentinel-2. So I want to just go with a simple model without worrying about interpolating the coarser resolution bands to the finer one and things like that. Just using the baseline bands. So this one, it will take probably a minute or so. It will, again, fetch the dataset collection from this ID, then search for labels and these assets within the AOI that we define. So it will find all the chips that are within this filter that I just gave the basically download method. So I'm going to wait a minute or so for this to download. If there's any question, even in the room or in the chat, please share before we go further. The next step is basically loading the data for modeling. And I should emphasize that in practice, you don't need to define any filter. If you want to get all the data, you just don't pass anything here. You just say dataset download literally. And that will download all the assets. So it depends on the usage, what you want to do, how you want to use the data. In this case, again, to be tutorial and fast enough, I just define some filters to limit that. So what's happening here is, again, downloading that tar folder, then unarchiving that, so read through the catalog. Behind the scene, just so you know, for those who are interested in the data engineering behind this, we are building a SQL-like database on your machine, querying all those parameters that they intersect with the AOI, the date and time, the asset types, finding all the asset links that I showed in the catalog, and then starting to download the assets. That's what happened in this, between here and here, we were basically building that SQL thing. Now it's downloading, so it found 415 files to download, which is basically 1, 2, 3, 4, 5. So 415 divided by 5. This is 83 chips. For each of them, we are downloading 5 files: the label file and 4 source, basically. That's how we ended up with 415 assets to download. And this will, the download speed will basically depend on your internet. On the end of this, the data is sitting on Microsoft Azure Cloud. So there is no bandwidth limit from there, particularly for this dataset size. It would be really on your machine and internet bandwidth. Again, all the methods are built into this. If the download fails, it will automatically retry. If your internet disconnects for a while, you come back to this after an hour, it will continue from where it left. All the information is stored locally for that. So don't worry about any disruption in your internet connection. The size? Good question. I think one of these information should be that. I think this one is the size in this case, because this is only, because this was the whole size for this one, for example. But good question. I feel we don't print the size for assets. Yeah, you see the speed, which is items per second, not necessarily kilobyte per second. That's what IT is for. So we are printing the number of items, so filter by intersection, getting the items and everything. But yeah, we are not showing the size. That's a good feedback. I can talk to the team.
But so on the first line, that wasn't.
That's only the metadata.
That's only the.
Right, so we only download, at the metadata level, you don't have any idea about the number of items. You just download the zip folder. For that reason, you just know the size. You don't know what is inside of it. Then after you unzip, you know there is actually 90,000 items within there, which is describing all the different chips and their metadata. And then we filter by them. We ended up with 415 assets, which are the actual GOT files to download. Yeah, but it's a good point about putting the size there. So this might take another minute or so. Any questions?
Ada pertanyaan lewat Zoom atau di sini? I just took that one. You know, we just go into the notebooks, just go in the time, but they can go to 2, 2, and 4.
Yeah.
Configure later on.
I mean, while this is downloading, I can tell you what we're doing next without running it.
Yeah.
This is basically a typical machine learning step from here on. So one thing I want to emphasize is, again, in this notebook, within 4 or 5 cells, you download your training data. And you literally, the next step is building your model. You don't need to worry about anything. I will also print some sample images here. You will see how the images look like. We do some exploration before building the model. But in this cell here, we are basically building a data loader for our package. The data loader will basically look at all the stack files that we have locally, find the asset names, which we downloaded here. It's being finished almost 96%, and then return those stack files. For the raster, we have the same thing. We have a load raster, which basically we use raster.io package. I mentioned the raster.io, it uses the open file, it gets the band, it returns that source data set basically. Then we get the item data set. So we pass all these 4 bands that we have to this get item data. It will call this load raster, load item stack, and we'll get all those stacked together, pass it as a NumPy array back to us. So this is just machine learning engineering, basically. This is the for simplicity, we created a class data set here because at the end you will call the class to load the data. But this would be the choice of the programmer how they want to load the data. In this case, we called it example data set just as simplicity. And here you would do this thing basically. You say this is where my collection is recorded. This is where that label collection is locally. For simplicity, we're only loading 5 here, but we can do more and train a longer model. You pass those items, you have all the train items, you create the example data set, that's the name of the class, which will have all your training data, and then you pass the data loader to that with a batch size and a shuffle. This is the parameters you use in machine learning, right? So the batch size and everything is defined here. 64, but we have only 5 items, so basically we only have 1 batch. There is not much happening there. And shuffle is just for during the training, you shuffle the batches basically. Let's see if this is completed. So this is almost done. It's stuck at the 100%. But this part is sometimes you even reuse these codes in different machine learning tools or pipelines you have. How much code you write here, honestly, it really depends on the user again. We try to write this in a very generalizable way. So we don't say, oh, this is only this specific data set we have. So that's why you see all the asset names are passed to the function. The entry point is the stack files, not the specific file name for this data set. So you can reuse these functions later on to load the raster, load the stack item, and generally create this class called dataset. This is ML specific, but I'm happy to answer any questions. Not much about Radiant. So load raster function return what type of object? Is it NumPy array? So here, what it returns, this is a NumPy array. So basically you say raster open name of the file as source. This is how you would work with raster.io. Because if you don't do that, you open the file, you need to also close it. In a Pythonic way, you would go with width, say is a source, and then this would read band 0 because it's, we know it's only 1 band, we only read band 0, and we flatten and we return this as a NumPy. It also returns what we call source profile. This is if you need to have the geospatial information for this. So it will tell you the bounding box, the projection of the scene, and things like that. But for the ML part, you would only need this NumPy array, basically. Yeah. Is the download completed? It might be.
Right, the very last bit.
Yeah. It might be structured crosstalk. My next step is easy. We just want to plot a sample data set here. So I will show a sample. Actually, we're showing the distribution here. We want to show the class imbalance before getting into sample visualization.
Could you explain why class imbalance is important for ML?
Yeah. So first of all, what we mean by class imbalance. So in this case, we have a cloud detection data set, which means in the labels, you have 0s and 1s for pixels that are cloudy and pixels that are not cloudy. 1 is cloud, I think in this case, 0 is non-cloud. This is written in documentation. If I go back here, you can see that. So this is the documentation for this data set that explains everything basically. 0 is no cloud, 1 is cloud, 255 is no data. So if you have no label, it will be missing data basically. When you want to build a machine learning model, it's important for your model to have, close some of these tabs, to have.
Terus nggak ada kembaliannya. Ya dan nanti aja sekalian si ibu juga lagi puasa.
Yeah, you would need to have enough samples from different classes. Class imbalance means you have an imbalance in the distribution of the data. Whether this is good or not, it really depends on the problem. In this case, it's a binary classification. Ideally, you want to have a balanced data set, which means the model is seeing enough number of cloudy pixels and uncloudy pixels, or cloud-free scenes. If you don't have that, it's good to be aware of that and make sure you evaluate the model correctly at the end, and look at what I will show at the end, confusion matrix and everything. You can implement things to mitigate the impact of class imbalance on your model. One is you discard some of the labels. So if you have too many cloudy scenes, you don't include all of them in the training. You just simply balance it kind of artificially when you're feeding into the model. The other one is to add coefficients to the model that would kind of lower the weight of the class that is highly represented in the data set. If you have, for example, 80% cloudy scenes, 20% cloud-free scenes, you want to make sure those cloudy scenes don't overtrain your model. You can add coefficients to that. You can add methods that is called dropout, which means you randomly remove some of the coefficients from your model to make it more generalizable and again less overfitted to your specific data set. So it's an exploratory step in the model training to make sure you understand the distribution of data before feeding it into the model. Why is this taking so long? Let's see how many I downloaded. So while that is downloading, we can go back here in the same folder. Now I have the tar file for the REF. This is just the name. As you see, the names of these data sets are the name of the institution and the name of the data set. This was NASA. This is REF, which is Radian Earth Foundation. Cloud cover detection version 1. And again, here you have test labels, test source, train labels, train source. So we are only using the labels and source in one of these, not all of them. Just again, to start with a simple model. Let me see. Download.
Yeah.
But I'm sure they're downloaded. There might be some final data claim that is stuck. Check that. I'm just looking to see where.
Biasanya kalau kelas sepi kayak gini susah.
Iya. Semuanya tegang.
Semuanya sedang bercakap.
You see these assets that are downloaded now. So each of these chips now have a band 4, band 3, band 8, band 2, band 4, band 8, band 3, band 2. And the reason we are storing these in separate files is that it will give you the option to pick and choose what bands you want to download. Because if you stack them all into one file, you're forced to download everything. Again, to make it simple, split it up as much as possible, let the user decide what bands they want to download. If I drag and drop one of these, again, in QJ, as we see, this is just one band 3, which is blue, green. This is green band from Sentinel-2. If you merge all the 3 bands, you can then see the optical data as well. So these are all downloaded. I don't know why the download is still taking long. And this is now the raster label, basically. Oops.
Could I ask a question?
Sure.
For normal imagery, those bands wouldn't really matter a lot. So for remote sensing scientists who are interested to use ML, having those different bands separated, what could they do with that?
So when you want to build a model, you basically use the bands as input feature. In this case, I'm going to use band 2, 3, 4, and 8, which is the red, green, blue, and near infrared in Sentinel-2 for cloud prediction. Your domain expertise will tell you, oh, what bands are more important for the target variable I'm interested in. Sometimes you want to use, I don't know, red edges in Sentinel-2 for crop. Many people use that. In this case, again, make it simple, go with 10-meter RGB and NIR would be good enough for cloud detection. But you may want to add the sewer bands, which is the short-wave infrared ones. So that's how you would interact with these bands at the end of the day. And depending on the data set, maybe some of the bands are not provided by the data provider in the collection. But because you have the bounding box and the time band, we can literally retrieve those from any other sources if needed. Or any other source imagery if you want to. I mean, in this case, it's not applicable because it's a scene-based cloud label. Sentinel-1 or Landsat 8, there's no value in them. But generally, this is how you would interact with different bands. I think I can safely stop this. This might be starting just one item that is failing.
Yeah.
Okay, let's try this way. Scroll down. So I stopped that because it showed 415 are downloaded. Let's see if it works. So this is the cell that I had all the methods and functions defined. So there's nothing happening here. Let's look at the class imbalance. So we are going to load 5 or 10, I think, images. And this is the distribution. So we have about 200,000 pixels that are cloudy and 125,000 pixels that are no cloud in that small sample that we loaded. This is definitely imbalance, but again, for simplicity, we might just continue with this distribution. But be aware of, hey, my model might be fitting more to the clouds, and you will actually see that in the confusion matrix later on. Because the more cloud you have, the more the model will learn about cloudy pixels, but not much about no cloud. Another thing to keep in mind is the no cloud is a very heterogeneous class, because no cloud means anything on the ground, right? It can be water, it can be soil, it can be building, it can be vegetation. But cloud is one class, or at best, very few classes, depending on the brightness and kind of darkness of the cloud. So you might want to have actually no cloudy pixels to be more than the cloudy ones. This again comes to your domain knowledge of what does each class mean before you build your model. And that's why I say this is the job of remote sensing scientists, not computer vision people, or at least people who are interdisciplinary. Without any domain knowledge, if you just start using this data set, you might just build a random model without knowing what you're doing. So that's what's happening here. For the model, again, to make it train fast and simple, this architecture is basically a fully connected neural network. So we are doing pixel-wise classification. Some neural network layers here, all of them defined based on the Torchio, a sigmoid layer at the end. So we get the basically binary classification out. Very simple, basically 2 hidden layer model. The training will be typical of the processes in machine learning, right? So you have a training loop that you will pass your data loader, your model architecture, what is your loss function, your optimizer, number of epochs, basically epoch 1 and the total epochs. In this case, I said 5 is good enough. We can get to these needs and nuts of machine learning, but for simplicity, assume you know what I'm talking about. Let's just run it to see what happens. The magic will be nicer afterwards. So this is now the machine learning training. So it's going to do 5 epochs. Epoch means in each epoch, you would feed all of your data to your model, find or optimize your parameter space, find the coefficients, do another one, do another one, do another one. After 5, it will stop. When you stop, it depends on you. You can fix it by the number of epochs yourself, or say, when I see flattening of the loss function, or after a certain number of thresholds stop. This comes to more the ML side of things. So in this case, again, this is the tutorial. I stopped it by 5. So we're already past through 2 of those. Questions on the chat? No. 3.
Is 5 usually like a conventional,
There's no convention.
there's no
It really
convention?
depends on model, the type of data, size of data you have, complexity of the model architecture. Yeah. there's-
So for like a binary classifier model like that, you wouldn't need so many, is that safe to assume?
I mean, binary is simpler. That's a
Yeah.
good point. Yeah, but as I mentioned, it is also good to know that the no class, no cloud
class
class
is
is heterogeneous.
Yeah.
So it is not binary you would think about them, right?
Exactly.
It's not like black and white.
Right? it's
So
not-
in that case,
not-
you might need more epochs compared to a binary classification problem, which is more distinct between the two classes.
So this is why it's important to have remote sensing scientists working with
Yeah,
data scientists.
yeah, knowing the domain knowledge, having good evaluation afterward, really looking at test tables, doing performance in any application. And this is just a simple cloud, but this is, I think, the simplest classification problem we can run in a remote sensing scene because clouds have a good contrast, at least with the background. So that's already. So the model is trained. Now we can do some visualization of the model performance. So what I'm doing here is basically picking a sample test label. I choose number 11, we'll see what it is. Then I will ask this function to visualize the false color NIR because it has good distinction between cloud and surface, the predicted cloud probabilities and the cloud labels. So this is what's happening here. So this was the input image. Specifically, I use the false color NIR so you can see the cloud ones. This was the true label from the data set. This is the model prediction. The model prediction is probabilistic. We haven't put a threshold on it. Noting that we just used 10 scenes, 10 basically chips, pixel-wise classification. Honestly, this is doing pretty good. But you can definitely feed more data. There's about 20,000 labels in this data set. And you can use a much more complex deep learning even model to build a better basically classifier. The focus for us again is to make the data set easily available to you. 5 cells, then it's your art and expertise to build the best model here, right? The goal for us isn't to build a model. We are not doing that many modeling as you see. It's really on the data engineering side of things. But it will empower you to build any model you want to do on these data sets, basically. Any other question? Oh, okay. Can QGIS be converted from DDO? Oh, that's a very QGIS question. Honestly, I don't know. I haven't worked with the CAD format.
Do they wanna, does this person wanna explain why?
Yeah, it would be good if you can elaborate more why you need to do that. Because I think DWG is the installer for Mac. You don't need necessarily a conversion. You can literally use that to install it. And if you're on Windows, you can install the Windows installer, which is the .exe file. You wouldn't be needed to do. And I think there is a Linux one too. So if you can elaborate a little more why you need to do the conversion, that would be helpful. Yeah. So the last part is the confusion matrix. So now I'm going to pass all the test labels to the model. The confusion matrix is what is basically how confused is the model. Literally think about it that way. You have 2 classes. You will see if you have a cloud label, what is the model predicting on average? If you have a no cloud pixel, what is the model predicting on average? If all the, let me plot this, then we'll talk. It's easier because it's a diagonal thing. But this will take a while because it's 78 images, but it's inference, so it's not as slow as training. We're just passing basically each item through the inference class I defined at the top, getting the outputs and labels, stacking them together in one list, defining the classes, creating the confusion matrix, and this is where we use the scikit-learn, right? The scikit-learn package has a good confusion matrix module. And Seaborn is used to visualize this basically. And then we pass it here. We put the labels and just doing some visualization. The ideal thing is, because this is a diagonal thing, all of your pixels that are no class in the labels are also, sorry, no cloud in the labels, they're also no cloud in the prediction. The same way for the class, but there's always some confusion and something broke here. Oh, because all data were downloaded, okay. Okay, let's stop at a fixed number here, maybe 44, because 45 there. Yeah, that download thing for some reason was starting one item. Yeah. Yeah, one thing that is happening in that download thing and you don't know is that we are doing parallel download. So it's not sequential. If you have bandwidth behind the scene is using more than one thread to download the data. For some reason, I think one of them was failing and it was taking longer. So that's the only thing happening. Yeah. So this is classification model, right? Does the image and the test data chipped first? And if it is chipped, how? What is the dimension? Yes. So everything is chipped here, and it is 512 by 512. So I can go back and load some of these in QGIS, and I show you after we are done with the confusion matrix. But yes, going back to the dataset documentation, when you read through, it will tell you everything about it is chipped. No, 512. I mean 512. So 512 pixels by 512 pixels. One of the typical dimensions in the machine learning, basically. Yeah. Going back here, this is
so much more confusing than normal.
yeah. So this is the confusion matrix. Oops. Too big to fit it here. So the color is basically showing the value. The lighter ones means better. So here we have no cloud and no cloud. So 68% of the no cloud pixels are predicted also as no cloud, but 32% of them are confused with cloud. The cloud pixels on average do better. 82% of them are detected correctly, 18% of them are misclassified. When you have more classes, this matrix will be even more kind of distributed and heterogeneous. This is really binary, so you know what is the model confused with. This is where you need, as an expert, decide, okay, what do I need to do next? Do I need to add more data? Do I need to make my model more complex, add more features? There is a little bit of, I would say, try and error and ad hoc kind of decisions to be made here. Given the size of this data set, I would definitely go back and add more data. We just added 10 chips, it's nothing, before even making the model more complex. The first thing usually in these steps is, if you can add more data, definitely add more data. Let the model see the wider distribution. If you are then limited by the data set size for any reason, practical limit and the compute power you have, there is literally no more labels available or things like that, then start playing with the architecture and making it more complex. Because the more complex you make your architecture, the more data you need to find those parameters. It's that trade-off there. It's not about, oh, let's build the best deep learning unit model with, I don't know, 500,000 parameters. You need 500,000 training data to feed to that parameter space. So that's the hype sometimes in machine learning. People want to use the most complex model. But the paradigm is always, you have the right data for that model or not. So that's what I would recommend. From here, go back, add more data, see how the model changes, and then if needed, then start working on the architecture.
Can I ask why you think the model is seeing faults when there aren't any? If you like, you think you have a why?
We can do again more investigation here, doing some visualization of what are those pixels. One of my guesses would be there are some of the infrastructure that are bright enough to be confused with clouds. Some of them might be just the edges of the clouds that are shallow clouds, not necessarily deep clouds that are bright enough and again are confused with the surface. Usually these are the things, again, coming back to the context here, that you know, for example, I remember I was using a time series of Sentinel-2 and filtering out, because you know Sentinel-2 has a cloud mask itself, but it's a horrible mask. But I was like, let's just use that. This was 4 years ago, before this data set was out, to just filter out any cloudy pixel. And I stacked 72 scenes over a year in one region and removed all the cloudy pixels in each scene. At the end, part of the image was all empty, even after stacking 72 images. I was like, okay, something is wrong with that cloud filter. I went back, opened some of the images. It was literally a huge kind of a, a factory kind of thing with a very bright surface that the model was always detecting that as cloud because it's just bright. The model was a threshold thing in the cloud detection. So this is the type of thing you would look in the model. What are the type of pixels that the models compute with cloud? What context you can add there? Maybe you can add another feature in the model, right? Here I'm just using the 4 bands. I'm not using any NDVI, NDWI, or other metrics or features there. Maybe you can add those as predictors, helping the model better learn the patterns between these classes. This is all the feature engineering and the art of the machine learning to make it happen.
Yeah, I asked this question because I think those are where the domain expertise really matters, and because you're training as a remote sensing scientist, that's why you're able to, have that sensibility of that confusion happening in the first place.
Yeah.
Which most of the brain members are also trained remote.
Yeah, another example of that is we put out a competition a year ago for crop type detection. We had similarly chips with crop types in each field labeled. It was, I think, 7 or 9 classes of crops. And people at the competition forum were asking, can we use because the data set is geospatial, right? So each pixel has a latitude and longitude. They wanted to use the latitude and longitude as a predictor. I was like, that doesn't make sense, because latitude and longitude is a fixed value for each pixel. If, I don't know, latitude 10, longitude 20 says this is a maze, it doesn't mean anything.
Yeah.
That is not a but to a computer vision person, anything in the data is a feature. I'm like, no, that doesn't make sense. You need to go through those kind of descriptions and knowledge sharing to make them aware, hey, that is not a feature. You should not use that as a prediction. If you do that, you're literally overfitting the data to that region and you're done. Yeah, you will build probably a very good model, but it's unusable even if you shift to the neighboring state in that region, let alone another country. So yeah, these things happen in the community. We see a lot.
There's a question for you again by
Cloud optimized, Steve. What is the advantage of cloud optimized? Okay, very good question. So GeoTIFF is basically, so let's start with TIFF. TIFF is a format like JPEG and PNG and others. You store images in there. It's lossless because in JPEG you store coefficients, not the actual raw data. TIFF is lossless, so nothing is lost when you store data in TIFF format. GeoTIFF defines some properties for geospatial data in TIFF format, like the bounding box, the projection, the dimension of the pixels, all of those properties. Cloud optimized GeoTIFF, as the name says, it is optimized for storing these data on the cloud, which is literally about how you write the metadata in the file. When you have a file, it's a binary object, right? So we have a section called header, which means where you are putting the metadata of the file. In the old GeoTIFF, the metadata is at the end of the file. So when you open it in a binary format, you have to read every single line, which includes all the data, and then you read the metadata, which makes it hard because if you have a scene of Sentinel-2, it's 11,000 pixel by 11,000 pixel. You don't want to read all of that to get to the metadata. In Cloud Optimized, you are forced to put the metadata at the top, so you don't need to read the data, you just read the metadata. And then you can pick and choose and say, hey, I know now the format of this object. I don't need to read all the pixels. I just need this bounding box within the center. I can just read that part. There are also things about visualization. So you put what we call overlays in the Cloud Optimized. So other than the 11,000 by 11,000, you might put a sample of 5,000, 5,000, kind of sub-sample that. So when you're visualizing that on the map, you can easily do the tiling at different zoom levels. You don't need to read the raw data. So that's just basically making it easier to use it on the cloud without downloading the whole object. There's a whole paradigm shift on that, and people are using more of that. Yeah.
I have a question. So this morning we already discussed on the data set and then model. And I know and so as ML models, right? And where we can see browse the models that are provided by the data. And also Radino also has some competition that already published for the is it that simply just go through the code of the winners and then we try and then get hands-on on the results.
Yeah, good, very good question. So let me start with the second one. As you mentioned, we run some competitions, and the models from those are actually hosted on the ML Hub GitHub. So let me put this in the chat. GitHub. So if you go on our GitHub, this is the Radian ML Hub one. You see several projects, but the ones that are for competition, and we link this to the competition page. So if you land on there, like Zindi or other platforms that we use for competition, you will see a link to this one. We have, for example, Spot the Crop Challenge. When you click on this, it will tell you this is the winning models from the Spot the Crop Challenge. This is the actual challenge on the Zindi platform. And these are the top 3 winners. Why this is the 2nd, 4th, and 6th place, not the 1st, 3rd, and 5th, we can talk later. But it was basically we had 2 tracks, we couldn't have winners and shared between the 2. So that's why the 2nd and the 4th and the 6th were selected as winners. But you see all the description of what the competition was, what was the score of the winners, and then each of these have their own metadata and description how to reproduce the results. So they have the requirements file there, how to set up the environment, what kind of hardware they use, notes about anything in the architecture, and then the code is fully there. And we have gone through reproducing all these results before putting them out. So you can easily follow these guidelines and do the same thing, because for the competition purposes, we have to reproduce the results. Otherwise, they're not going to be awarded. We can't just accept their submission of the prediction. We need their model. That's the enforcement there. This is the basic we have done in the last couple of years. But now going back to your first question, we are adding the model repository to the ML Hub now. So why are these not there yet? This is a transition we're going to make in the next 6 months. Making sure from now on, all the competition models go on ML Hub directly. So you don't need to find a GitHub repo. You go to the ML Hub page and you see those models. We have done that with one of the models now. So if you go on ML Hub, this was the dataset page. On the models page, we only have 2 models now. The tropical cyclone model. This one is from the competition we ran in 2020. So this is a deep learning model for crop type classification that uses basically Sentinel-2 time series. Again, there's a documentation for this. There's a UI citation similar to the dataset form. But how you would use it, we are adding more tutorials on this. This is very much MVP product, as I call it, minimum viable. You have the inferencing runtime. So if you click on this, you will land on a GitHub page that has the model and will tell you what are the Docker files. Are you familiar with Docker concept or no?
They did land a bit.
Yeah. So everything in this model repo is Dockerized. That's the enforcement. Everything should be containerized. Generally speaking, we use Docker now. And then there are basically these files that will tell you what should be ported to the Docker for input data, output data, there are folders and everything. And then the actual model checkpoint is here too. So the final model checkpoint is that trained model object with all the weights. And this is sitting actually on a GitHub folder, but we just put it in the catalog itself. So, oh, this is going to download. Yeah, you just downloaded it. But you can see the link from here. Down there, you see at the bottom right, GitHub.io. This is on the GitHub page, basically. You can see all of that. We have also linked this to the training data. So you know what training data on ML Hub was used to train this model. This is again about provenance. We don't want to just put a random model out there. It should be clear to the user what was the source data that this model was trained on. So you can use the source and labels, both of them, to go back and look at the reproducibility of this model. This is in the Stack API. I think this is just the more metadata about this. This is the level we have done this. Actually, one of our team members is doing the reproducibility example here. So we are going to have a notebook. Emmanuel's work on that. We have a basically notebook coming up soon that will tell you, okay, this is a model there, how I'm going to show you to go after reproducing the same result, retrieving the model using it. All the methods are available in the Python client, so it's not like we don't have anything out there. If I go back to the client here, if I click on ML models, all the methods are now available. We just haven't put a Jupyter Notebook tutorial thing. We have a simple one I will show you, but not an extensive one. So if you retrieve the ML model, similarly, you can list what is out there. If you pass the model ID, you can fetch it. You will get the assets for that, and the assets is basically the checkpoint, the main one. And then from there, you can see the inferencing image, the training data target, the training data target assets, basically. And this is the data set. This is the collection. We have the notion again there. And then other properties like the title, license, and everything. fetching the model metadata, you can do that again from the getting the model by ID. And then you can also look at the general assets and next. This is just a general description. Back on our GitHub repo, this is where we have the tutorial, I remember. Or it might be in the Microsoft one. Let me see. I think we have put this on the Microsoft repo. We haven't put it back in here yet. Yeah, the model retrieval is on the planetary computer that I want to go to next. I will show that next. But there is a sample notebook there that will show you how to retrieve it. More tutorials, but definitely are coming up. This is a pretty much new feature for us. Yeah.
Just a time check, it's 11 a.m. Sekarang sudah 11. Technically, we're supposed to actually start with the planetary computer before that. We actually have a coffee break. But I just want to spend the next 2 minutes asking any of the Zoom participants. Kalau Zoom participants ada pertanyaan, langsung bertanya saja. Bearing in mind that this is the precious time that we have now with Mr. Ahmed, that will not happen again anytime soon. So don't be shy, jangan malu. Langsung bertanya saja. I know that this is all very new for many people. So if you feel lost or you feel like you want to ask certain questions, do feel free to ask. And I'm sure that Ahmed will be happy to filter any questions by email if there's time. Or you
Slack might be better.
Slack. Yeah.
Yes.
Join the Slack channel.
Definitely join the Slack channel
Join the
because
Slack channel,
you
please.
can post the question to everyone.
Yeah,
not
everyone
just me.
will reply. Yeah. What project?
Oh, the link, yeah, I can do it there. It's bit.ly /
No, only Slack. Sorry, no Discord. You don't use Discord, right?
Discord, no, we don't use
No.
Discord, no. ML Slack. I know if I'm correct, this should work. Oh, actually, because I'm on Slack, this might not work here. Give me 1 second. Yeah, okay, so here's the Slack sign up link. Or I put the full link, that's okay.
Thanks,
Yeah, join there, and then there's a general channel in the Slack I can show you quickly.
Kalau ada pertanyaan yang bisa langsung tanya saja lewat Slack, Rina, bukan hanya ada Ahmed, tapi ada yang orang yang lain yang juga tertarik tentang geospatial data dan AI.
Yeah, this is basically the Radian ML how Slack is based. You see some specific channels, but there's a general channel for people to ask questions and everything. You can also directly message any of us. I think Cindy is also on that workspace, but in general, I'm there. But if you put in the general channel, then any of us on the team can quickly get back to you. If you put it to me, there's a bandwidth limit that how many messages Ahmed can answer. Better is to put it on general, then you see that we tag the right team member to get back to you. So yeah, definitely explore this opportunity. And you can also then connect to others. You will, if you look through here, you see people are talking about various things, their projects, questions and things like that. There's also a space here about events. So events and opportunities, people post about workshops, fundings, events and things like that. So it's pretty much an open community for people talking about machine learning and earth observation. Yeah, you have about 1,000 members now. So definitely use this resource. I think it's generally a good thing to have. Yeah.
Kalau tidak ada pertanyaan, mungkin kita bisa lanjutkan untuk planetary computer. You can continue the planetary computer.
I need a 2-minute break, but yeah.
You need a break?
Myself, just using
yes.
this. But other than that, yeah, I can start. Someone is joining. So any of you who join, I get a notification.
Saya Bu mau bertanya Bu.
Ya, langsung tanya saja.
Terima kasih atas kesempatannya Bu ya. Saya di sini juga awal untuk belajar tentang quantum GIS. Sebelumnya saya menggunakan ArcGIS ya untuk pengolahan data citra satelit. Yang saya mau tanyakan untuk mengolah data spasial, apakah mungkin berbeda dengan menggunakan quantum GIS ini atau ArcGIS? Mungkin ada perbedaan dari data spasialnya Bu. Maksudnya apakah mungkin begini, data dari data spasial ini dengan menggunakan ArcGIS, perbedaannya dengan menggunakan quantum GIS itu, Bu? Demikian, Bu.
Bisa jawab.
He asked about the difference using ArcGIS and QGIS in processing data spatial.
I mean, broadly speaking, if you have geospatial data locally in your machine, there's no difference what you use, QGIS or ArcGIS. There's a cost difference, of course. ArcGIS is paid. QGIS, I don't see any value in using ArcGIS. I might be a bit opinionated about that, but if you're not using much of the infrastructure behind ArcGIS, which is their huge data catalog, their cloud scalability and things like that, QGIS is good enough. You don't need to buy a license to ArcGIS. But if you're an institution, you want to have a tile server, a database, a SQL, and you don't have necessarily an engineering team in-house, ArcGIS has a good off-the-shelf solution. That's where you would use ArcGIS. If you look at around the world, many government agencies use ArcGIS for that reason, because government agencies are not data engineers, right? So they buy a good license to ArcGIS, it has a good support system, and they just care about where is my data pipeline coming up, putting it in the right database table, and then visualize it or serve it to the users there. So that's the paradigm thing. Programmers are not usually using either of those. They just do everything in Python. But the more kind of end users, application users come to the QGIS, ArcGIS thing. I wouldn't recommend either of them for any kind of machine learning. Although ArcGIS has the Python package in there, if you're learning machine learning, I would encourage you to do it in the Python itself than ArcGIS, because otherwise you will be stuck in ArcGIS forever. The formatting is only specific to ArcGIS. You can't use it outside of that. That's the problem. There's a question from
There's a
Muhammad.
question for Ibrahim. If you go up, he says he has an error in the simple model training.
I have an error and try. Reagan and have simple model training. Have problem online. Or there is authentication error. Oh, you need to put your API key there. That's the problem. So in this line, here instead of your API key, you need to paste your API key like myself. So that's the error you're getting.
I already did.
This is in this cell, or where do you get the error?
In the fourth line, the fourth script. Yeah, this one.
Does he want to share his screen?
Can I show the script?
Please, yeah, share the
Please share
screen.
screen.
You can share your screen.
Yeah, but you can see the Iqbal screen. Oh.
Okay. So scroll up where you have your API key added. Make sure that cell is run.
Yeah.
Okay. Can you rerun this? We make sure it runs successfully.
Okay.
The process cannot access the file.
It's being used by another.
Oh, do you have another notebook running at the same time?
No.
Because that's what the error says. This is not about authentication. It says that the database table, the ML Hub stack assets.db, it's being run by another one. Is any of the other two notebooks you have open running now? No, in the same tab. You see the yeah, right there. Yeah.
Or close it.
Yeah.
Yeah, maybe also shut down the kernel on the left. So right click on the notebook on the left in the file menu on the left. Yeah, the other one. Yeah, right click and say shut down kernel. Yeah, scroll down. Yeah, right there. And also the other one. Oh, this one was this one. Maybe
and run it again.
And then go to tabs or to kernel at the top. Yeah. Do restart and clear all outputs. Let's go from scratch. Yeah. No, the third one.
The third one. This one.
The top one.
Yes.
Yeah. Okay. So let's rerun everything from the top.
Okay.
Okay. Okay, so what is the error now? Did you by any chance deleted your API key?
He did.
Yes, I have this one.
Oh.
Yeah. That's right.
It ends with 6. Go back there. 68461.
Okay.
Oh, you're missing a number 1 at the end of the key. You haven't copied it fully.
Wow. So, wow, you notice.
Oh, okay. Okay. I use this one.
Wow.
Thank you.
Does it work now? Does it work now, Iqbal?
No,
Yeah,
try again.
Iyalah, 3 ganti 1.
Yeah.
Okay, okay.
Yay.
Okay, now another error. What's that?
So you are programmer.
Now you have the deviation. Okay, now do the kernel restart again. It should
Because
work.
it's new. Oh, still same.
No, this is the kernel issue because it was running
Oh,
at the
because
same
it's
time. Yeah.
Oh.
Okay. Before I was using this one copied and the one is not copied. Okay, thank you very much.
Sure.
Mantap, Iqbal. Terima kasih. So now I think we should have a 15 minutes break so that our instructor will have the break time that he deserves. We'll just cut down on the next steps, and then we'll come back and talk about planetary computer.
Okay.
All right.
11.
See you back at 11.
We can do 11:20.
Okay, let's see you back at 11:20 a.m. 11:20 jam. Terima kasih.
Jam 11.20.
Dimatiin aja.
Hah?
Dimatiin.
Dimatiin?
Ya.
Enggak lah, biar kelihatan ada Rob yang serius.
Oh.
Suasana kelas.
Oh.
Ngobrol dong, ngobrol.
Bisa mute saja sedikit yang untuk.
Oh iya, mute aja, Pak.
Kenapa mau di-mute? Tes suara panggilan kepada mahasiswi Pak Hartanto dari tes ada? Tes.
Ada 3 orang.
Ada 3 kelompok katanya 6 orang ya. Mahasiswi KB dari ITS bimbingan Pak Hartanto. Pak Hartantonya nggak ada.
Karena juga lagi break.
Lagi break.
Hari ini jam 12. Ya, hari ini.
Kalau Nadira dan kawan-kawan, Nadira, Elizabeth, Nurul, menyimak nggak Nadira?
Tentu. Enggak, maksudnya nanti yang kalau ya kita nanti dimatiin.
Go this place, so I should find another place.
I think we can just go there.
Yeah, it might be crowded.
No,
So 12:30.
if we go at
Nurul, gimana kabar Nurul?
Alhamdulillah, Pak.
Ngikut dari kemarin?
Baru ikut hari ini, Pak.
Oh, tapi ini bisa ngikutin?
Ngikutin masih dari jam 10, Pak. Jadi masih mencoba.
Kalau Elizabeth?
Hadir, Pak.
Gimana, bisa ngikutin?
Ya, tadi saya juga ikutnya dari jam 10. Nyoba ngejar ngikutin pace-nya, tapi masih banyak error sih, Pak.
Oke. Nah, Dira, 24 giga bisa ngikutin komputernya?
Ngikutin, Pak. Masih nyoba-nyoba juga.
Oke. Sebagai informasi untuk teman-teman yang nggak ngikutin kemarin, itu dasarnya udah dipublish juga di Mapin YouTube ya. Jadi silahkan cek-cek atau nonton yang hari ini juga itu ada di Mapin YouTube, di kanal Mapin YouTube di YouTube. Jadi silahkan dicek-cek ke sana.
Halo semua yang untuk yang kembali ke workshop ini. Sekarang mungkin kami mau mulai tentang tutorial untuk planetary computer. So Hamad, do you want to introduce what planetary computer is?
Yeah. So first, why we are doing this, and then what it is.
Right.
So far we talked a lot about ML Hub, basically a repository, a library for training data, some sample notebooks, how you retrieve the data, how you train a model. But the next natural step is building a more scalable model. And usually in that case, you're limited by how much capacity you have on your local machine, right? whether it's disk space, whether it's CPUs, whether it's scalability in terms of parallel processing and things like that. So there's a lot of cloud infrastructure, as you know, out there. Particularly the main three players are Amazon Web Services, AWS, Microsoft Azure, and Google Cloud. Each of these entities or companies have two types of offering. One is what we call bare metal cloud, means you go there, there is a cloud service, you figure out your own machine, your own data loaders, your own data pipelines, your own databases and things like that. On AWS, Azure, and Cloud, and Google, we can do that. The second tier is for those who are more application oriented. There are some already established infrastructure for you to use. The, I think, famous one in remote sensing is Google Earth Engine, right? Many of you might have used that. Already has the data catalogs of many satellites and other types of geospatial data. You go there, there is an interface, you can do programming. On Microsoft, the equivalent of that is called Microsoft Planetary Computer. As the name says, they want to be a computer for planetary level kind of computes. On AWS, there is no similar example, but there are a lot of machine learning specific packages or kind of services you can use for the same thing. I mean, SageMaker, we were talking with a person the other day, it enables such a thing, but it doesn't necessarily have the same level of interface you would have on Planetary Computer or Google Earth Engine. The reason I decided to demonstrate a little bit of capability on Planetary Computer is twofold. One is, first of all, from a technical perspective, this is a very new infrastructure compared to Google Earth Engine, which is from 2010. And it has used many of the newest technologies and resources for scalable model development and generally analytics, not just model training. Secondly, it is integrated with ML Hub. So if you are in Planetary Computer, you can easily access many of the services and training data from ML Hub. We work with them closely. What I'm going to demonstrate today is because of more than one, I think many of the questions and discussions yesterday, my take was there is a limit on how much compute resources we have access to scalable things. So I will demonstrate a sample notebook on Planetary Computer, which is about how you would retrieve a large number of scenes, for example, from Sentinel-2, do a mosaicing, do some analysis on that, and come up with a median scene. It's a lot of scenes. You will see I'm doing a lot of compute there. And we will use a technology which is already installed on Planetary Computer. It's called Dask. I mentioned again this yesterday when we were chatting around the meeting. Dask is basically, I'm not going to get to the, again, cloud DevOps part of it, but it's basically a way for spinning up multiple machines or cores and assigning tasks to them in parallel, and then being able to retrieve the results back. The nice thing about Dask is after it is set up, which requires probably one engineer or cloud person to set it up for you, on Planetary Computer is already installed. You don't need to do anything. From a programmer perspective, is literally a one-cell Python code. And then you have access to that Dask machine. I will show you how to use it on Planetary Computer. So the goal of this session is basically going on Planetary Computer, showing how to spin up a Dask cluster, and then running a very heavy kind of data analysis on some Sentinel-2 scenes. It's not about machine learning training. I tried to keep it simple, so we deal with more with Dask than machine learning here. But it's to show the art of possible on there. Footnote, how you access Planetary Computer. So Planetary Computer is by default open, but you have to request to sign up and get approved to get on board. It's like the early days of Google Earth Engine. I think even Google Earth Engine now is like that. You sign up, you submit a request to get, this is me, I'm doing this, I'm going to use it for this purposes, and then they give you access. After you get access, there is no cost in using them. It's similar to Google Earth Engine. But it's much more Pythonic, and you will see that it is all Jupyter Notebook based. So I will demonstrate that for today. If you haven't already signed up, you can. I mean, you can submit requests now, but it's I don't think you will get approval right away. But it has all the notebooks as a tutorial thing on the machine already. So if I share my screen, you will see what happens there, and I will put the link in the chat. So let me speed up the share thing. So this is the link for the Planetary computer, basically. There's the chat. And then if you don't have access already, you will go here, say request access. It's a very simple form with a couple of questions you fill in. But otherwise, I will go to the hub, which is basically a Jupyter notebook server for you to do analysis. Again, all geospatial focus and all Python friendly. There's a lot of tools and documentations here if you want to explore, but given the focus on one notebook, I will jump into the hub. So when you click on the hub, it will come up with it says what type of machine you want to spin up. So at the beginning, you have actually option to do R as well, but we're going to go with Python. You can do a CPU machine, you can do a GPU machine with PyTorch, you can do a GPU machine with TensorFlow, or you can actually do a QGIS on the cloud. This is the newest one. I haven't tried it, but they have this now. We will go with a simple CPU machine with 4 cores and 32 gigabytes of memory. This is the default thing it comes. And let me zoom in here so the text is actually larger. Yeah, okay. Yeah, and is anybody familiar with Pangeo, what it says here, or no?
Wait.
So Pangeo is a framework, let's call it that way, that has brought some open source Python packages together for this kind of deployment. Specifically, Jupyter Server, Dask for this scalable analytics, and what is called X-Array. X-Array is a Python package for doing multidimensional analysis. So multidimension is pixels in 2 dimensions, bands, and time. That's multidimensional already, right? So X-Array, Jupyter Notebook, and Dask on the cloud. It's an open source project. Microsoft is just using it as a way of deploying their thing. So that's why you see the name Pangeo there. So I'm going to say start here. This might take 30 seconds or a minute to spin out. This is basically spinning of a cloud machine for me now. As you see, when you are logged in, there's nothing as a programmer you do other than just say, yeah, I need this machine, spin it up. And then it will be all Python after that point. You're already on a cloud machine. Yeah, this is not all of the cloud. It's 4 cores and 32 gigabytes of memory. But it's a starting point to know how to use Dask, how to do things. If this is good enough, we can just use that. If you need more, then you need to pay. Yeah, beyond this limit, you need to pay Microsoft to use heavier machines or things like that. But with this simple size of machine, it's for free. Let's see if the rest of the board is sleeping. We can get a machine.
Iya, karena kalau pagi baru Amazon udah power banget.
So it's coming out. And this is my local one. I can close this.
Selamat siang Bapak Ibu. Mohon menunggu dulu dikarenakan di pusatnya sedang mati lampu, jadi break dulu sekitar 2 atau 3 menit. Terima kasih.
Maaf yang semua partisipan, maaf yang di sini ada power outage, jadi yang wifi-nya baru bisa masuk. So we just wait for a while. And thank
Hi everyone, maaf yang tadi ada
Okay, so just before we disconnected, what I was doing was basically waiting for the planetary computer instance to spin up. This is where you will land after that. As soon as it spins up, you will basically see a Jupyter notebook server, or in this case, a Jupyter lab, basically. It's very similar to what you would have locally in your machine. It's just on the cloud now. That's the only difference. There are a lot of good examples already there and quick starters. So if you want to go through them, you can try them out. I will pick one example specifically about how to work with this task thing that I mentioned. And this is named Tutorials Cloudless Mosaic Sentinel-2. Basically, we are gonna stack a lot of Sentinel-2 scenes together to create a cloudless mosaic over a region. As you can imagine, this can be a heavy computation, depending on the number of scenes you select, the AOR, the size of that, and everything. And that's where we are going to use Dask in particular. So a little more about Dask. Dask, it's a very, again, community, open source driven technology. Now there are also enterprise level kind of products for that, but the basic kind of packages are open source. And it lets you define, I'm just going to explain this in 1 minute as simple as I can, what they call a graph, meaning that a graph is a compute kind of sequence of things you want to do, but you don't necessarily run it, you just define it. For example, you want to say, take band 2 and 3 of Sentinel-2, creep it to an area, derive, for example, an index like NDVI out of that, get the NDVI value, then plot a time series of that over that area. These are a set of sequence of processes you want to do. You define this in task, but you don't ask it to run. You say, okay, this is just the math. They call this graph because it can be different processes stacked together. And then you will define your data. Say, okay, this is where I would read the data. So know that this is the input data and everything. When you are ready to do the compute, you ask DAS to go in and basically run that process over your data. What DAS will do is, first of all, spin up different nodes, different machines. If those processes can be parallelized, it automatically does that. You don't need to do anything. It figures out what can be parallelized and it does that. And then parallelize it in terms of loading different data sets at the same time. If you have like 10 different AOIs, it can be 10 different nodes at the same time. But again, as a user, you will see you just have one cell in Python that you will define task. The rest of it is the simple NumPy, Python, any other Python packages that you would use would work with task. That's the beauty of using this thing. It might sound a little bit scary at the beginning, but honestly, if you spend, I would say, less than a week just learning about task, your whole life will change after that, because it's just a monster in terms of how it does computes. So the purpose of this one, basically we want to create, as you know, we are living in a tropical region here. Having cloud-free scenes, it's hard to find. So we want to create a mosaic, meaning stacking multiple scenes together and find or construct a cloudless scene. What we will do that, we will create a time series of images for a point on Earth. We stack them together in one single array, compute the cloudless mosaic by taking a median of those. That's typically what the algorithms do, and then visualize the results. For the dataset, we'll use basically Sentinel-2 level 2A, which is already available on Planetary Computer, so you don't need to do anything for querying the data outside of this ecosystem. Typical packages that are used, NumPy, I assume you're familiar. Xarray is what I was just talking about before we disconnected. This is another Python package for multi-dimensional data analysis. It is not specific to geospatial data, but it has very good features you will see later on about geospatial data. I don't know if you're familiar with NetCDF, one of those formats for data storage. You know, in NetCDF, you define dimensions, you define coordinates. That very same concept is mapped in Xarray. So in Xarray, you can define dimensions and say, oh, this is time, this is coordinates, this is bands, and then have name for those dimensions, meaning, oh, this is latitude 10, 10.1, 10.2. And when you want to do compute, you just refer to those dimensions. You don't need to think about Python indexes. That's the beauty of it. Rather than thinking about, oh, this is a slice 10 of that thing would be band X. No, you say, oh, give me band red. And Xarray is aware of what is band red and what dimension that is, what coordinate is that. So this is another Python package which has come up, I would say, in the last 3 years or so, and very much used in the geospatial these days. Raster.io is another one that I mentioned. Stack is basically stacking, putting together stack items. So that's stack. People are cute with their name. PyStack is another stack client for querying planetary computer data, and planetary computer is basically the API here for retrieving Sentinel-2 data. You can kind of skip that part of the puzzle, how you retrieve the data for now, and think about the task for a second. This is multispectral, kind of XR spatial. This is another function you can use for median calculation. Finally, this is the Dask thing. So from Dask Gateway, which is the name of the package, you call Gateway cluster, which is basically the cluster of nodes you need. I will run this first, so this is just importing packages. The second one is basically creating what is your Dask cluster, or the cluster of nodes that you will use later on for compute. We are processing a large amount of data, as I said, and to cut down on the time, we'll use Dask cluster, which adaptively scales and adds new workers or remove them when you don't need them. So it is pretty much on-demand scaling. It doesn't unnecessarily spin up machines and just let them run for no reason. And that's important, particularly when you are running it on your own instance of any cloud, because you don't want to have machines running for nothing. There is another introductory notebook here if you want to go through, but we'll start with this one. So here you create what they call a gateway cluster. It may take a minute to do this. You get the client from that, and then you define how many cores or nodes you want to have. Here we say we want at least 4 of them running at each time and maximum 24. But if you don't need them, it will kill all of those 20 extra ones and stay at 4. It doesn't spin up more than 20 basically. So let this run. One thing the Dask has, it's a nice thing. It has a visual interface that you can see how many nodes are running. So I will show you how you can do it in here after this run. So this is now basically the link to our Dask cluster. Okay, I'm going to copy this. Because Dask is available here, there is a button here. If you're familiar with the Jupyter Generate, right? So this is the file ones. These are the tabs that are open. Here, there's now a Dask one because we already have Dask installed. And if I paste this link, you will see all the different functions and you can see what is going on in the Dask cluster. How much memory is using, what are the keys there, CPU usage, GPU ones, the whole graph that is doing the data processing, and many other kind of metrics about the cluster. I'm gonna pick up the CPU. There's nothing happening here because we are not running anything. So we will come back to this when the process is actually running. Similar concepts what we were doing with ML Hub. So we want to go define an AOI, get some Sentinel-2 scenes out of that. So you define an area of interest, similar notion here. We convert this to bounding box because this is how the API and Magic Computer learns about packages. But Rastrail has a good function that you convert this AOI to bounding box. This is just different formatting of the same thing. This is their Python client for searching the data. So you pass the API endpoint. This is for them. They don't have a client in the notion that Radiant ML Hub has, but they have a very similar Stack API. So it's everything is based on Stack. You say, this is the API. I want to search over this bounding box that we define for this date time, which is the whole 5 years from 2016 to 2020. The collection I want to search for is Sentinel-2 level 2A. I want maximum 500 basically batches of data. And I want to filter already by cloud cover, which is at the scene level, anything that is less than 25%. Again, this is a standard that 25 means 25% here. It's not 0.25, the example I gave yesterday. If you run this, this is just searching the catalog, just giving you items. There's no data downloaded here, okay? Metadata search, basically. He's found 138 scenes that we need to stack on top of each other to do the cloud, basically the scene mosaicing. And this is where Dask will come in next. So these items still have some clouds over them because we know the 25% threshold is still a lot. So we want to create our cloudless mosaic here. The area is, oh, I forgot.
Redmond, Washington.
Did it say? I think it says, yeah, it's in Redmond, Washington, near Seattle, where Microsoft is based, basically. But we can change this now to an area of interest ourselves. Let's do that, actually. We don't need to go with the I'm gonna pass this bounding box. Okay, let's use our own bounding box. How many scenes? Hopefully it's not a ton of them, otherwise I'm gonna make it smaller. 286, not bad. So 286 scenes overlap this area in Jakarta over the 5 years, which have at the scene level less than 25% cloud. We are gonna then stack them together. Yeah.
5%.
5%? I mean, we are gonna stack them, so let's see what happens. Then we'll have too many scenes to do. I would like to have more scenes actually. Okay. That's where the art of Dask comes in, right? So we're going to load this to Xarray. Xarray is going to stack them, you will see. And then this is what is using stack basically. So we will get all the items. This is basically getting the URL of those items. Here I'm building the stack, which means I want these 3 bands, again, RGB bands here in this case. We do red, green, blue because we want to be RGB, so 4, 3, 2 for that reason. This is how you would chunk the data. If you have used NetCDF, you can have a definition of if I'm storing my data it might be 10,000 by 10,000 dimension, but please chunk it to small pieces so I can retrieve smaller chunks of data. That's just for data set storage. And for simplicity, we just increase the resolution to 100 meter. But otherwise, you can use the raw data as well. It's just making the compute a little less extensive. So this is now the stack of data. Nothing again is loaded. This is just the metadata. And this is what X-array shows you. X-array says, hey, I have this multidimensional array, 3 bands, 20,098, 20,098 pixels. And then I have 286 of those stacks together because 286 scenes over the 5 years. This will take about 33 megabyte of basically memory storage later on in the chunk size, but the array size is actually 28 gigabyte, the whole thing stacked together. But nothing is loaded now, it just gives you the estimate. And now we're going to say, hey, we want to keep all that data in memory. I think with this size, it should work, but let's see. Yeah, so far, reasonably good. Now the actual art happens. So you see in the CPU, something happened here. When I said data persists, it started loading the data, but it was so fast, you will see quickly, these nodes are loading the data, putting it into memory, basically. Each line is a CPU, so it will be between 4 to 24 because we defined the minimum and max to be 4 and 24. When this is done, all of the machines will be killed. That's it. And this data is now in memory for us, basically. The next thing is, okay, now that we have all the data, we want to run the compute. So the data is loaded. Dask helped us load all that data in parallel. Otherwise, 286 scenes, if you would load them in sequence, would take much, much longer. But Dask helped us doing this in parallel, basically. Now we want to do the compute thing. So this is the art of X-array. Data is this structure we have here, right? And it has all the basically coordinates you would want. The time, the band, the X and Y. So the data set shape is aware of these dimensions. You can then call X-array and say, hey, I want data, but I want the median of that over dimension time. So you're telling that without knowing what is the shape of that thing, hey, just grab the dimension of time, get the median of that. And then you pass compute, this is for Dask. If you don't pass this compute, nothing will happen. It just creates that graph that we talked about. Compute means literally go and run this thing. So I will run this thing and then jump on the CPU to see what happens. This is now another, yeah, all of those cores are now active doing the compute analysis for us. Over 286 scenes at the pixel level, which was almost 2000 by 2000, that's 14,000 pixels. So that's a lot of compute. And probably within a couple of seconds, we will have all the results there.
So do you think this is a good option for brain, given what Pak Agustan kemarin Anda bilang ada sedikit masalah untuk compute, betul? Jadi yang itu yang Anda itu yang untuk yang menyelesaikan masalah Anda yang bagus atau enggak?
Wih, kita akan tes. We will get a testimony later on after we succeed.
This is good for R&D to start, I would say. I put it that way. If you want to put into operational pipelines, you would need to have an instance of this on your own cloud thing, because then you can customize memory, disk space, and everything. Here you're literally doing R&D. You want to play with data, you want to do these mosaics, you want to build models. You're limited by memory and disk space, as we were just talking. So there are some limits into that. But it gives you an entry point to see, okay, how can I scale with Dask? Because Dask is really the powerful these days for doing this scale. We have all this data on the cloud, but we are not using it because we don't have the right, basically, compute resources. And these are now helping us do that. We internally now at Radiant, we have our own Dask thing on the cloud, which is basically an Azure. So this is done. So all of those 286 scenes were median average pixel level, and we can now visualize that scene. This scene might be a little big, so that's another point. This is the, there are still clouds here after adding 286 pixels together.
Tapi bukan daerahnya Pak Harto.
Bisa disebut.
We choose only Jakarta.
Nggak ada.
Yeah, this is the area I chose.
Yeah.
Yeah.
Oh.
Yeah, I can go larger. That might take a little
No,
longer. That's it.
She want to more smaller.
Oh, smaller. Oh, sorry. We can go smaller another round quickly.
Iya,
Iya, tinggal di Zoom.
Iya di Zoom nggak ada.
Okay, that's the method.
Ya pasti nggak ada lah orang Jakarta.
This one is good.
No, smaller.
Small. Jakarta
Smaller?
only. Yeah.
Small.
Even only this area. only this area. Menteng area.
This is good.
Yeah. That's the one.
Okay. This will be much faster. So let's go back.
Paling bawah tadi Menteng. Marina.
And then this area, get the data, 129 scenes, so that's much faster and smaller data, you see? Yeah, so persist, median,
Udah selesai.
running against. Not that fast. But
Wow.
still has 129 scenes, so.
The question from Daniel, if this is the
Kayaknya banyak
same
juga,
notebook
guys.
and the same report.
No, this notebook was already on the planetary computer. So when I went to the planetary computer, there's a tutorial folder there, which comes up when you spin up your machine. And this notebook was already there. This is not at GitHub. I mean, it is, the source is on Microsoft's GitHub repo, but at the end, you get it right there in the Jupyter notebook there. So it's called Cloudless Mosaic Sentinel. This is still working. The task itself, the software is free. But when you're spinning up on the cloud, the machines that use it, you pay for those. But the software is free. For what?
For running this right now.
This one, no, the planetary computer is free. And that's why it has limited access, right?
Yeah.
It has 32 gigabytes and 15 gigabytes of disk space, 32 memory, 15 disk space, and only 4 cores. And to get there, you need to request access and approve and then go there. But usually the application is just you say who you are, what you're doing. They're trying to not onboard commercials at this time, which makes sense. So that's why you need to go through the application process. But there's no cost to this, no. So the median is ready.
What are we seeing?
Here's what?
Probably.
Probably I gave the wrong area.
Yeah,
This is still too big, right?
Oh yeah, this one.
Yeah, I should have said this one.
How come it's different?
Maybe I didn't delete this correctly. Right? So, okay, this is deleted. Let's do one more time. I know probably what's happening. Okay, let's try one more time. I think they don't cookie cut it to the area. They are doing the Sentinel-2 scenes that intersect the area. That's the difference, probably. Yeah. Okay, I know what's the problem. Yeah. See, you're getting a sealed in 129. So they are looking at that bounding box and get one Sentinel-2 scene that intersects with that. That's why we get the whole area. We need to add one more line to cookie cut it to that region. Yeah. But we can increase this one to 20 by 20. Oops. We can zoom in to see what's going on in Jakarta. And that's good. But I can save it out and maybe download it then later on. That might be something. Save. What was save? Okay, I need to look up the save later on. Let's go to the next line and then I will come back and save this for you. I can send it over. The next thing to know is on the X-array thing, you can also say, hey, I want median, but I don't want to mix winter with spring. Give me medians for each month separately. That whole thing that I described is this thing. You don't do anything else. You just say, hey, data group by time.month. Similar concept you have in pandas. You can group by a feature. The feature here is time, which is month. And then you get median of that and compute. So in this case, we are going to have 12 composites. And again, you see this task thing will start populating the cores. But But at the end, you will get 12 scenes, and this is I ran over the old area. We can't run it now. You will get 12 mosaics for each of those regions that we just talked about. So definitely, I would recommend starting even locally using X-ray because it's a whole game changer in terms of how you do data analytics. This should show up. Yeah. So this one didn't have enough scenes here, but you see for each month now we have a mosaic. For some reason, yeah, the last one is gone. It might not have enough scenes. Yeah, it probably didn't have any less than 25% scene. Yeah, that's interesting.
December is always cloudy. Is that what you're saying? Yeah, it's raining now.
Yeah. So over the 5 years, in December, we didn't have a single scene that was less than 25% cloudy.
That's crazy.
That's crazy. Yeah.
But what about time zero? Why is it only half?
I think probably because, so this is what's happening, I guess, at the beginning. This area that we selected is overlapping more than one scene of Sentinel-2. And here what's happening is that the left one don't have anything less than 25% again. So nothing shows up in our filter. If we increase that, we will see some scenes popping up there. And being close to December, it makes sense that January is like that. Yeah. So yeah, that's the art of X-ray and DASK. Basically, my final point is the tools are out there. You would need to just bundle them together, use X-ray, use DASK, stay in Python, and then put it on the right ground. If in the future you decide you want to use this whole Pangeo thing that I talked about, but deploy it on AWS, you can do that as an institution. You are not tied to using this. But you will lose the data catalog here because they have all the basically data sets already there. Let me go back to the catalog. The last thing we can show. Here, when you say data catalog, you see Landsat collection, MODIS collection, Sentinel-1, Sentinel-2, some of other sensor data on the ground. There's this global biodiversity information facility. I haven't used many of these. There's some labeled images of wildlife conservation, even non-geospatial things.
Is it because Microsoft AI funded a lot of this project?
This is all funded by Microsoft AI for us. Yeah, 100%.
That's why they have all this data sets
Yeah.
that are very specialized.
And they're regularly adding more data sets. So this is just a snapshot of what is available. This is all the DEMs, the digital elevation models for different regions. Some of them are more fine resolution depending. I mean, for example, in the US, we have LiDAR data, so they have included LiDAR as well. But globally, I think it's the ADOS one and the Copernicus DEM. There's demographics, US Parent area from MODIS and others, and other imagery from Aster level 1. Those are the harmonized Landsat Sentinel-2. This will be global. This is not yet global. They're harmonizing these two satellites together to come up with a better time series and spatial resolution. They have the specific AOIs. They have published the data, but the global one will come this year. And more MODIS. Planet NICFI is also there. You know, Planet, the monthly mosaics that are free for specific applications. This might be another area to look into. I think definitely Indonesia is covered in there. Definitely Indonesia is covered in
and I don't know if anybody knows this, but Hamed told me that Planet now provides base map every month for NGOs, is it non-profit?
Yeah, NICFI is basically for non-commercial applications. They call it related to forest, but honestly, agriculture and their definition is also related to forest. Conservation is related to forest when you read the footprint of the licensing. But these are monthly mosaics at the 4.7 meter spatial resolution that planet imagery comes. We are also using it for fusion project. Yeah. And they have two products. Yeah, the Microsoft building footprint that they have released, it's all available here.
They just released their building footprints for the whole continent of Africa.
Oh yeah, yeah. Microsoft is going a little crazy. Yeah.
Okay, water.
Yeah, there's also the JRC Global Surface Water. This was a product came out a couple of years ago. They're hosting it in here. And this dataset was supported by Google, as you remember, but it is hosted on Microsoft as well. Some of the flood maps from Delta-S.
Oh yeah, it's Google that released the building footprint. It's not Microsoft.
No, building footprint is also
Microsoft too.
I think both of them. Yeah. They are competing against each other for that.
Yeah. I mean, so like given that all these enterprises are doing so much, like I guess what Radiant does even more is that you provide training data too, right?
We are agnostic to where you do your compute. That's the whole idea about us. You want to be on Planetary Computer, be on that. You want to be on Google, be on that. AWS, on that. We are agnostic. We built integration with Microsoft because they were interested and we thought it's a good thing to do. Google is not interested in doing that. Google is being Google. Microsoft is more friendly. And AWS is trying to stay away from compute things like this. They don't have that. They have data catalogs. They have SageMaker, which is more infrastructure, but they don't have anything close to this. They're taking a different approach. But one thing we are going to do, and we have already done some of that, is that our data is now on Azure, and some of it is also on AWS. So copied on both clouds. Because when you are doing model training and you're reading the data multiple times for each epoch, if you're reading from another cloud, there will be some network dependency and delays for that. So we are going to put the data on multiple clouds so you can pick and choose which one you want to read from and make it again faster and easier for you to retrieve the data. Cool. That's all from me. Question?
Yes. Kalau ada pertanyaan, mungkin Anda bisa Anda bisa langsung bertanya. Kalau Zoom participant ada, karena ini yang program yang terakhir. Setelah ini sudah selesai. Jadi kalau ada pertanyaan, yang langsung tanya saja sebelum selesai workshop ini.
You mentioned that Radiant ML Hub is agnostic to using the Google or the Microsoft, but I know the Google have like GE training set something, training tutorial, but do Planetary have the tutorial?
Yeah, the example I just showed, the Jupyter Notebook is from their tutorial.
So
it's on us, yeah.
Not from a Radiant.
No.
Okay.
This is the Microsoft themselves.
Okay. Yep.
Any more questions? Pak Dayuf, Pak. Halo Pak Dayuf.
Which is best easier by using Google Colab, Python, GitHub?
I think he's asking, is it easier to use Google Colab or Python itself? Is that one?
I mean, Google Colab is a good thing to get started with, particularly because it has the Python installed. It doesn't give you much resources. I think it's half of what you get on Planetary Computer, basically. But it's a free tool. Many people use it for education purposes. That's how I would use Google Colab, not necessarily for research, and definitely not for production. So for educational thing, you want to do something in class, get some people to get hands-on. Don't worry about Python installation. Google Colab is the best to go. And you just need I think, Gmail account to access that. There is no charge for it. So yeah, in that case, I would recommend it. But if you want to do more research work, yeah, Colab may not be as reliable for that. Yeah, you would rather do it locally.
For Planetary, since when they are up and running?
Planetary Computer was released 2 years ago, no? But majority of the data sets were added in the last year.
Okay, 2 years ago, that's
Yeah.
it.
Yeah. It was something cooking up for a while, but it's 2 years ago.
Okay, this is the first time. Excellent.
Daniel asked questions again.
How many data sets in remote ML Hub? I think there's many other remote sensing data sets for ML training, like Kaggle and GitHub. So what is the plus value of Radiant ML Hub? So very good question. How many we have now? It's about 37, 38 data sets. The value is that, first of all, on Kaggle, you are not specific to geospatial data. You have everything in there. I would say it's a jungle. And the geospatial data that are there are very limited. The GitHub thing is, it is not discoverable. So the first thing that ML Hub provides is, it makes it easy for you as a user to discover what datasets are available. Yeah, we don't have everything added here because we are still spinning up a lot of new catalogs. But as we grow and we add more, the idea is you can have an API interface and a good search that you would find what are the existing datasets out there without the need of remembering all the various different GitHub repos. Secondly, we are storing the data in a format to make it as ML ready as possible. As you notice in the notebooks I went through, literally the first couple of cells you went through, you get the data, and the next thing after that is your expertise and art to build the model. That's how we distinguish from them. It doesn't mean that they are not doing the right thing. No, they are for different purposes. Kaggle is built for competitions in any field. So the data formats, the structures, the way you access things are not for geospatial data, which are very heavy. You can't host 60 gigabytes of data on Kaggle, never ever. We have now a new training data set coming up from Planet. Open access is 2 terabytes of data. Ever impossible to put that on Kaggle. You need the type of filtering and accessibility we have built on ML Hub to interact with those data. And we are going to have more of that as a community. So that's what ML Hub is trying to address.
It probably also is also not synchronized to Stack too, right? Given the
yeah, definitely Kaggle is not using the Stack because the Stack is specific to geospatial. Yeah.
All right. So I just want to be mindful of time and energy. Saya sudah tahu yang semua sudah capek sekali. Jadi untuk next steps-nya, saya last question. Okay, wait.
Oh, is there will be a charging? Okay, good question.
No.
So our business model is that the user should not pay for accessing the data.
Yes.
We might charge data providers in future, but not the user. So if
Yes.
someone wants to put their data on ML Hub, we might say, hey, support us, because someone at the end of the day should pay for this thing, right?
Yes.
It's not going to sustain forever. But the business model is the end user, particularly non-commercial end user, should not pay for that. So that's going to stay as it is now. Yeah.
All right, with that good note, I would collect all the email addresses. I think I have them from Zoom. Is that possible, Robbie? Because I would send next steps for what we can do to continue building this community. I just want to be mindful of time and energy. I know it's already 12 p.m. Some of you also have do your afternoon prayers. So thank you so much for being here. It's like, okay, Google is different though, right? Google is a big tech corporation.
We can talk about that offline.
Yeah.
You get problem with the power outage again.
Yeah, then you might want to send your inquiry via Slack to Radiant ML Hub. And with that, thank you so much for this, and the certificate will be sent to you, and I'll be in touch via email about next steps. And thank you so much. Terima kasih banyak sekali. Yeah. Did we just end?
Pak ini ngomong dulu. Pak, siapa yang ngasih speech? Terima kasih.
Can we? I think Pak Agus.
So thank you very much, Ibu Dr. Cindy, Dr. Ahmed. Terima kasih banyak. Thank you very much for your time flying away from United States, come here, and then teach us and inform us, updating us so many new information for us, and hopefully it can be useful for us, for the community. And before we close, maybe is there any comment from the audience, the beneficial or the benefit to
One open mic,
maybe from students, or maybe insight from Pak Hardy? Because Pak Hardy is the one of the bring the new technology in the geospatial since 1970s in Indonesia. Pak Hardy ada komen Pak Hardy?
Open mic, Pak, open mic.
Pak Hardy. Seems like two people actually open their mic.
You still mute your mic, Pak. You need to click the mic.
Okay.
Oh yeah,
Yes, we hear.
Okay. Dr. Ahmad and Dr. Sendilin, it is nice to be joining your workshop. It is very useful for us and then hopefully that whatever you give this 2 days workshop will be useful for us. Pak Agustan, terima kasih atas undangannya, dan semoga semacam ini bisa diberikan lebih banyak lagi, karena di kampus-kampus kayaknya kok terbatas gitu ya. Jadi kesempatan ini yang sangat bagus sekali untuk terutama asisten-asisten yang banyak yang akan turut. And Cindy, have a nice trip back home or wherever you will go, because and then hoping that you said that in summer you will be visited again Jakarta, and then hopefully that you can visit Bandung also. Terima kasih semua.
Terima kasih banyak sekali Pak Hari untuk yang hadiri itu workshopnya, and you kept your camera open the whole time.
Yeah.
We felt like we were something as listening to us.
Pak Hardi yang harus bertanggung jawab, soalnya Pak Hardi yang memasukkan teknologi-teknologi baru ke Indonesia.
Responsible for the digitization of maps in Indonesia.
Yes.
It's because of you that Indonesia is able to be where it is today. So
At least I will monitor everything what Mapin will give the presentation. Thank you.
Terima kasih Pak Hardi. Mungkin dari generasi milenial, generasi muda, ada yang mau disampaikan? Yang paling muda, student.
The younger generations.
Ada perwakilan dari generasi muda?
Open mic atau open
yang
space.
Mau ada?
Itu ada Dina Dwi Anugrah, itu ada.
Volunteer mau menyampaikan?
Mukanya ada.
Para student. Mungkin ke depan diskusinya kita ini akan ada kurikulum nih, khususnya untuk yang berbau geoscience.
Bagusan Dinar itu Pak.
Dinar. Halo Dinar, ada yang mau disampaikan Dinar?
Open
mic.
Enggak sih, kami ngikutin aja karena pembelajaran di perguruan tinggi untuk bidang teknik sipil hidrologi itu banyak sekali menggunakan citra satelit. Jadi kami tertarik untuk bagaimana memperoleh data-data scientific data ini dapat dimanfaatkan untuk kegiatan pembelajaran S1, S2 maupun S3 di perguruan tinggi. Ini yang kami ingin lakukan gitu, makanya kami mengikuti dari kegiatan-kegiatan MAPIN ini. Makanya tadi saya sudah catat semua alamat-alamat kalau nanti kami secara online mau untuk komunikasi yang lebih dalam lagi tentang bagaimana mengakses data-data, ketersediaan data-data yang ada di Indonesia ini. Itu aja.
Terima kasih Pak Dinar. Itu emailnya Bu Cindy. Kalau mau kontak Pak Dinar, hubungi ke sana, Pak.
Oke, gimana? Kami dari Universitas Sriwijaya.
Sriwijaya.
Palembang.
Oh,
Cindy pernah ke sana survei?
Ya, saya pernah ke Palembang. Bagus sekali, enak sekali bebeknya. Palembang. I think after the break,
kami di teknik sipil untuk bidang kajian hidrologi. Jadi BKU manajemen yang kami lakukan dengan itu mencoba mencari akses kemudahan data-data secara online gitu yang bisa dimanfaatkan oleh para mahasiswa, terutama untuk S3 maupun S2-nya, karena sekarang S1 juga udah banyak sekali memanfaatkan data-data citra satelit tersebut. Ya, nanti kami akan berkomunikasi terus terang aja dengan BRIN, dengan BRIN. Jadi kami akan mencoba memanfaatkan data-data terutama yang open source ya. Kalau mahasiswa kan yang dicari open source tapi bisa multi temporal gitu. Karena kalau tidak multitemporal, yang jadi masalah ini sampai saat ini di dalam semua penelitian dan sebagainya, data yang dimanfaatkan itu menggunakan data-data yang lama, terus kemudian teknik interpretasi dan sebagainya juga menggunakan data lama. Jadi hasil daripada kajiannya itu tidak valid tentu saja. Itu aja yang kami ingin jelajahi, bagaimana memperoleh data-data secara open source. Itu aja.
Selamat siang, Profesor Dinar.
Iya. Pak Ardi ini, Pak Ardi sering kerjasama dulu dengan saya.
It was long time ago.
Iya.
Oke, ada lagi?
Oke, terima kasih banyak Profesor Dinar dan Profesor Hardi Kusama di atas komennya. Kalau yang muda-muda mungkin masih sedang menyerap ya, Tony ya.
Nanti kita bikin tutorial.
Ya, kita buat tutorial. Jadi semua materinya ada di YouTube channel Mapin RI,
Dan repo-nya untuk GitHub.
dan reponya segala macam, semua online karena sekarang kan semangatnya online semua ya, online, kemudian sharing, data sharing, kolaborasi, dan kita harap semakin banyak kreativitas atau aplikasi-aplikasi yang muncul dari kolaborasi. Mungkin itu yang sebagai komunitas di Mapin yang harapkan gitu ya, kita berusaha menjembatani dari researcher, kemudian para creator, student, ataupun para pengguna atau penikmat data seperti Pak Swas yang katanya sebagai penikmat data itu bisa untuk ke depan seperti itu. Oke, sebagai informasi tambahan, sertifikat sudah diumumkan oleh Pak Robi, bisa diperoleh dari link di bawah ini. Nanti tunggu informasi dari Pak Robi untuk sertifikat dan yang lain-lain. Oke, terima kasih. Thank you very much for your attention. And now officially we close the 2 days workshop on the artificial intelligence from Global South. And please give applause for Pak Hanet. Yeah. And then there is one memento from Mapin that will give by Pak Oni, and from IEEE OSTM Bu Marina. Please give to
This is from Brain.
Oh ya.
Pak Hanet dulu, Pak Hanet dulu.
From Bu Marina. From IEEE to Pak Hanet. Please.
Thank you.
Picture.
Maybe in front of the camera.
Yeah, in front of camera.
Yeah.
Camera
In
there.
front of that.
Yes.
Ini kelihatan kok.
In the front.
Di sini juga kelihatan. Di sini. Enggak di sini. No. No, here. The camera is here.
Can go this way.
Ya. Ya di sini.
Almost there. Thank you.
Just one.
Wait. Okay.
Picture.
Oh, this picture.
Oh, in here.
Okay. Smile. Okay. Dan Romapi, Pak Oni itu Cindy.
Yes.
Thank you.
Sama-sama.
Wow. PhD. Wow.
Udah,
thank you.
Terima kasih semuanya, and I'll be in touch via email, and you'll receive the certificate soon. Thank you so much, everyone. Take care. Selamat.